dia, né? Meu nome é José Tabosa e, em nome da comissão organizadora, quero dar as boas-vindas a todos os presentes. Vamos dar início ao simpósio sobre a colaboração científica na área de física entre a França e o Recife, né? E este evento faz parte das comemorações dos 50 anos do Departamento de Física da UFPE. Now I have to switch to English. So, good morning and good afternoon, everyone. On behalf of the organizing commission, it's a great pleasure and honor to open this event, which celebrates the 5th anniversary of our physics department. Let me start by saying that along all these 5 decades, we have developed a strong scientific collaboration with several French researchers from different universities. Some of them are present here today. And this has played a very important and crucial role for the scientific consolidation and recognition of our physics department. Of course, as it was pointed out by Professor George Budeb, I'm sure we all would prefer a presential meeting for this kind of celebration, but unfortunately that was not possible. So I really would like then to welcome and thank all the speakers for their effort to attend our virtual symposium, and especially the academic authorities that are represented in this section. So let me announce and thank our Vice Rector, Professor Moacir Cunha, the Director of our Academic Center, Professor Claudete Pereira, the Head of our Physics Department, Professor Alexandre Ricalde, and our Emeritus Professor, Professor Cidi Araújo, who will present a brief overview on the France-Recife Collaboration. I have also invited the General Consul of France in Recife to participate in this opening section, but unfortunately, due to his very tight agenda, he could not come. However, he promised me that tomorrow we will have the participation of some representatives from the French consulate. Indeed, on behalf of the Physics Department, I also would like to acknowledge and thank for the financial support that we have received from them. This was very important for the realization of this event, so I really appreciate it. So I wish you all a very good symposium, and I hope we will learn more about the history of our department. And I really hope you enjoy all the talks. Okay, now let's try to follow the schedule. And in this opening, I will invite first the head of our physics department to welcome the participants. So please, Alexandre, Professor Alexandre Ricalde, you have the screen.
Okay, thank you. I did my PhD in France, which are not part of this collaboration, but I have a very good memory of this wonderful country. So on behalf of Physics Department, I would like to thank you for your participation in this meeting. Most of you are part of our history in one way or another. So we are very happy and honored to be with you. I wish you all a very good and fruitful meeting. So thank you.
Okay, thank you, Alexandre. Now I will ask the director, Professor Claudete Pereira, the director of our academic center, to welcome the participants. Please, Claudete.
Thank you, Tabosa. Hello, everyone. First, I would like to thank the organizing committee from this Symposium France-Recife Collaboration in Physics for inviting me to attend this opening ceremony. It's my pleasure. I'd also like to congratulate Physics Department on its 50th birthday. As director of the Center of Exact and Natural Sciences from Federal University of Pernambuco, I would like to welcome all professors, researchers, and students. I'm sure that the symposium will allow strengthening this well-established research partnership between France and Recife. I hope soon you can share our knowledge and expertise in person, healthily and safely. And finally, I would like to apologize, but I will soon have another meeting and I will need to leave this room soon, sorry. And thanks for your attention.
Okay, thank you, Claudette. And now I'm happy to ask our Vice Rector, Professor Moacir Cunha, to welcome the participants. Please,
thank you very much, Tabosa. I would like first to greet Claudette, Professor Claudette, the head of our Center of Exact Science and Nature, and also to greet our Professor Cidi Araújo. Very nice to meet you, Cidi, and to see you again once more. I'm very happy. And also Dr. Alexandre, Professor Alexandre, head of the Physics Department. In fact, despite the COVID, it's a very important year for us in the Federal University of Pernambuco, 2021, despite all the constraints and all the sanitary crisis. I would say that because we have first the motivation why we are here, 1/2 century of existence in the Physics Department. It's really very proud initiative, and we are very happy to make this ceremony today. But we have also 75 years of our university. 75 years ago, we put together a set of schools in Recife. I mean, the School of Law, School of Medicine, School of Engineering, all of them more than 100 years old. Today, I put together and started the Federal University of Pernambuco. And this year, 2021, is also the year of the 100th anniversary of the godfather of the education, the Brazilian education system. I mean, another important scientist, Paulo Freire, and the science of education. So physics comes with all this group of ceremonies, and that we are starting until the end of this year to bring and to call the importance of the science. It's very good to have the physics department. It's very important. I would say that one of the most important pillars of the science in our university, and we are all the community very proud to have that. In fact, we have many challenges. We have to face many challenges in our existence today in the Anthropocene period. We have, for example, what we're living now with a health crisis. We have all the challenges coming with the warming planet as the global warming and climate change. We have many different aspects that can be faced only with international cooperation in very strong science. We believe in science. We need science more than ever. Our planet and the mankind need science. So we have to improve and foster the international cooperation, because it's very clear that's the only way to face all those science, all those problems, challenges, and also the overcome of this problem. And I would, in particular, to give you some word concerning our French colleagues. I have a particular attachment with the French country, and I am very happy to see and to know more about this cooperation between the Federal University of Pernambuco and the French institutions. So let's keep on the same track. Let's keep making a good science. Let's keep all the improvement we got until this half of century, and let's move on. Congratulations to all of those that made this beautiful trajectory in the physics department, and congratulations to all of you that will arrive along the track, and we will improve more and more the physics in our country and in our state of Pernambuco and in the Federal University of Pernambuco. I will finish by wishing a long vie to the physics department, and we can count with the administration, and we are very, very happy, very happy to have you on board. OK? Merci beaucoup à tous les collègues français d'être ici. C'est vraiment un moment très important pour l'Université fédérale de Pernambuco. Je suis très heureux d'être avec vous et d'avoir votre disponibilité de fêter aujourd'hui ces 50 ans de département de physique de notre université. Merci beaucoup à tous. Je vous souhaite un très bon meeting au cours de la journée. Et, malheureusement, je ne serai pas avec vous tout le temps. D'où aussi, comme Claudette, professeur Claudette, il y a un problème d'agenda, mais je serai de ma pensée. Toute la journée, je serai de ma pensée avec vous. OK? Merci beaucoup et une bonne continuation. Thank you very much and very welcome to this symposium. Very, very, very happy to be here with you.
Okay. So thank you very much, Professor Moacir, for this inspiring initial speech and in warm words for our department. So thank you very much. Now we move on, and I would like then to ask Professor Cid Araújo, our emeritus professor. And I just want to say that Professor Cid was one of the founding fathers of our department. And actually, he has participated actively, very actively on this collaboration between France and Recife. So he will present a brief overview from the historic point of view of this collaboration. So please have the screen, Cid.
Okay, Tabosa, thank you. Bonjour to everyone. I thank Tabosa for the invitation to say some words. And he said to me that I should not go beyond 10 minutes. So I decided to write something to read here in order to not pass this time. So I'm going to tell you part of the history of the physics department and part of the history of this interaction, Recife, France, in optics, lasers, and atomic physics. In some way, I participate of this interaction since the beginning. I'll start with my first connection to Universidade Federal de Pernambuco. My link with the UFPE started when I entered in the engineering school in 1964, March 1964, which is a date, a special date. After 2 years, I conclude that I would not like to be an engineer. And after finishing my undergraduate course on electrical engineering, I decided to move to Rio de Janeiro to study physics. My colleague, José Rios, went also to PUC Rio, the place where I went to, at the same time. And we stay in contact with other colleagues, Fittipaldi, Marco, and Mauricio, who were at USP São Paulo and started making plans to initiate a research group after going back to Recife. There was no physics research here at that time. In July 1971, I was hired by the UFPE, and with the other colleagues, including Sérgio Rezende, who was hired in 1972, we initiate the implantation of our research laboratories at the physics department. José Rios did not return to Recife at that time. He went to MIT, but returned to Recife in 1977 after finishing his PhD there. At MIT, Rios met Martial Duclos, who interacted with him during his PhD project that consisted of laser spectroscopy of gases. Well, I remember that Martial and Rio, they published some papers together at that time. Martial was a postdoc at MIT. It occurs that also Rios made contact with Claude Cohen-Tanougy, who was spending some time at MIT at that time. So I would say that that was the beginning of our Recife-France collaboration. Perhaps it was 1975 or 76. Rios might remember it better. I wrote this yesterday night, so I cannot be sure about this date. Could be 75 or 76. In January 1976, I went to Harvard University for a postdoc during 2 years to work in linear optics and returned to Recife in January 1978. Then, with the help of Rios and Sérgio Rezende, I started the nonlinear optics lab here. Therefore, in 1982, appears the possibility to establish contact with French groups, and we saw that it would be a good opportunity for our optics labs in Recife. Then, I think that it was arranged by Martial in some way, in contact with me and in contact with Rios and me. We planned and we received a visit of a group, a big group, during 2 days. The group was formed by Claude Cohen-Tanougy from École Normale Supérieure, Claude Moniz and Gérard Manfred from CEA, Center for Atomic Energy of OCE, Sylvain Liberman, who was director of the Laboratoire Aimé Cotton, Jacques Lucassic from École Polytechnique at Palaiseau, and Christian Bourdet from University of Paris, Nord. So that was the group. They arrived here during one weekend. We worked on Saturday in the physics department. And after that, they moved to Rio de Janeiro. In Rio de Janeiro, we organized a symposium involving people from Rio de Janeiro and from other places. So immediately after the symposium, it was proposed a project involving Recife, UFPE, PUC at Rio, Catholic University at Rio, and University of São Paulo at São Carlos. And Universidade Federal of Rio Grande do Sul. The French institutions that were participating on that was the École Normale Supérieure, Paris, Center for Atomic Energy, OCE, Laboratoire Aimé Cotton, École Polytechnique, Palaiseau, and University of Paris, Nord. The project was financed by CAPES COFECUB for about 10 years. It was not a usual project of CAPES COFECUB. The coordinator in France was Claude Cohen-Tanougy, and after some time, the new coordination was Serge Arroche, both from École Normale Supérieure and both Nobel Prize winners. Not at that time, but after a few years after that. Okay, and in Brazil, the coordinator was Humberto Brandi from PUC, Catholic University in Rio. He was the coordinator for the Brazilian universities. In the frame of this project, José Rios went many times to France. I went only 3 times. I went to École Polytechnique at Palaiseau and Université Paris Nord. But Rios was the one who was able to develop series of works with Martial Duclos and his collaborators. Several colleagues from France visited Recife for seminars, short courses, and some research interaction. For example, the coordinator, Claude Coentanugi, came here several times, delivering courses based on his research. And he was, in fact, the coordinator for some time. I don't remember exactly how many years, but for a long time in the project. As a consequence of this interaction, some students went to France. I remember that José Tabosa, spent a time at Viltaneuse during his PhD, a kind of sandwich stage. Marcos Oriá and Fernando Oliveira, who finished their MSc here, both under my supervision, and went for a doctorate in France. One former student from École Normale Supérieure, Arturo Lezama, came to Recife for a doctoral thesis under supervision of me and Rios. Anderson Gomes went to Center of Atomic Energy at Orsay. After, at that time, he was a young professor here in our department. Along the years, we had other projects from CAPS, COFECUB besides that one. I remember that in atomic physics, there are projects which were coordinated by Rios, by Tabosa, and perhaps by Daniel Felinto. My formal interaction with the French groups was not in atomic physics area. Initially, I had some, from the formal point of view, I had some CAPS COFECUB projects with Marcel Poulain, who was a chemistry in the chemistry department of Université Rennes. We performed experiments in Recife using glass samples prepared in France. In my case, a long period of scientific interaction started in 2002, after my visit to Université d'Angers at Angers. I have been collaborating with Georges Baudebs for almost 20 years now. I went to France many times for short visits. Georges came to Recife several times. In 2016 and 2017, I spent 6 months at Angers as visiting professor. In about 18 years, we published about 20 papers in good journals and several communications to conference. Our work always involved students at Recife and Angers. The work, unfortunately, the work stopped because of the pandemic, but we are still writing papers for publication with basis on experiments done at Recife. More recently, we start collaboration with Pierre-François Brevet from Université Lyon, who with the regular exchange visits of researchers and students. So that gives you an idea about the interaction in this area involving lasers, nonlinear optics, atomic physics, some solid state physics. And to finish, I want to say that for about 40 years, me and colleagues from the physics department have this productive collaboration with our colleagues in France and hope that it will continue for several more years. I think that, Tabosa, I did not exceed my time. I'm not sure, maybe you are controlling that. But, well, I will finish here saying that I wish to all of us a very productive meeting today and tomorrow here. So, Tabosa, thank you for the opportunity to say these words. Thank you for everybody who is hearing this talk.
Okay, Sid, thank you. It was perfect. Let me then thank all the academic authorities for their warm words in this opening. And now I think we should move to the next talk, which is a kind of keynote talk that will be presented by Professor Martial Duclos. I think he's there. It's for me really a great pleasure to introduce Professor Martial Duclos. Martial is an emeritus professor at Université Paris-Nord e diretor de recherche do CNRS. Il faut dire classe exceptionnelle. He has a vast scientific career, and it is almost impossible to try to enumerate all his academic and scientific achievements here. But among his many distinguished titles and positions, I just wanted to mention that he's member of the Russian Academy of Science and of the Bulgarian Academy of Science. He was a former president of the French Physical Society and also the former president of the European Physical Society. Martial has a long history of collaboration with our physics department, as I think he will mention in his talk. And in fact, he has published a large number of scientific papers with many of us. Finally, I just want to mention that Martial was the one who proposed the year of 2005 as the International Year of Physics. And as most of you must remember, due to his strong link to our physics department, he also proposed that the closing ceremony of that event to be held here in Recife. And I think that was a great moment for our physics community. So without further ado, thank you, Martial, for being with us, and please have the stage, or better, the screen.
Hi, are you hearing me? Is
Yes.
that okay? Yes.
Yes.
Thank you for the introduction, and I would like to thank you and the organizing committee for the invitation. Good morning for the people in America, like I'm right now, and good afternoon for the people in France. So I've been asked to do some introduction, so I would like just to make a kind of review of how I see the collaboration between University of Paris-Nord and Recife, and also the extension which happened after. So I have to find how the way of, I think that's here. Are you seeing that? Yes, I think so. So this is, I would like to speak about all these collaborations that we have between Recife and Nord-Est in general, and the Paris-Nord University and the Laser Physics Lab. I mean, first, some historical view. I mean, as we have said, I mean, it has been said partly. I mean, in fact, our relationship started with Rios in MIT in the year 74-77. At that time, I was as a visiting scientist and postdoc in Michael Feld and Ali Javan lab. Ali Javan was the inventor of the gas laser. And Rios was a PhD, doing his PhD, and he got it in 97. And our work was mainly on laser spectroscopy of molecule and coherent transient. I show just two publications, common publication on this done in ammonia using NO2 lasers, and on some laser spectroscopy and transient coherence in ammonia. Now, I would like just to say a few things about the starting years. I have to say I did not agree with Sid with what he has said. I mean, the real history is that it started by a PICS, I mean, a cooperation program between CNRS and CNPq. It's not a CAPES coffee cube. It was started because the CNRS was decided to have some exploratory mission in optics, and then they approved that, and it was at that time, as it was said by Sid, led by Claude Coentanucci and Umberto Brandi. So I wanted to find some picture of Claude and Umberto, and I did not find not much, but this one is in Recife in 2005, as you say, that the closing ceremony of the International Year of Physics was held in 2005 in Recife, and you have Umberto and Claude. Claude is okay, is not very well taken, but at least we have the two organizers together. Now, also, what was the lab at the start? What were the lab? The lab were, in fact, our lab, but also the laser Kessler, the Kessler-Brussels laboratory, which has what's called Laboratoire de Spectroscopie Hertzienne, and the lab of optique quantique in École Polytechnique. For instance, Aimé Coton was not included, which is interesting. I mean, I don't know, I cannot tell you why. But, and in Brazil, it was mainly Cook and UFPE, I mean, and the physical departments. So it's just objective as given here, and laser spectroscopy, non-linear and quantum optics, laser cooling, and it was first scientific stay for research, but after there was a CAPES funding coming for PhD students, and that's the way that we have a few students coming to, for instance, to Ville tunnels. There was no special emphasis on doctoral formation at that time, but we have some sandwich thesis and work. The final Brazilian-French workshop was in January 96 in Rio. I would like to say a few things about the context. When I say two Norths meeting, the two Norths are meeting, I mean that we have, in fact, two difficult regions for the development of science. I mean, Nordeste was at that time a relatively poor region of Brazil, which was not well developed. And it was not like Sao Paulo and Rio. And the Department of Physics was founded in 1971, as we are now looking at the 50th anniversary. And the optics section was very small at that time. I would say mainly Sid and Jose coming back from MIT. And just to say the difficulties, I found this picture that I like with Rios. I mean, when we are coming in the morning at the physics department, I mean, the same time you have the people, I mean, the cowboys, I mean, coming with their cows on the campus, because at that time it was possible to put the cows on the campus. And Rios wanted to show me that he was able to do it. We have many, at that time, we have many special visitors. I mean, I remember seeing some snake, I mean, in the camp, not in the campus, yes, in the campus, but not inside the building. And I would like to remember that you have termite in your room, experimental room. Paris 13 is different, but is in some way was in the same type of position. University was founded in '69, just after the '68 events, And there was a strong humanity component, very weak science one. And the environment is north of Paris, and it was quite difficult and still quite difficult, in fact. So we have similarities with UFPE, but we had optics and laser lab relatively strong because we have a good group coming immediately. I mean, with Bernard de Comte, was after went to the minister, Christian Bordet, Michel Dumoine. So we have some good group, but we have to try to find our place with respect to Paris Center and Paris South, I mean Paris Orsay. The peak started very quickly between our two units, I mean laser physics lab and the physics department in UFPE. The reason I say that we needed more. And so in 10 years, we have 7 stay of researchers from LPL in Recife and the same number of stay from Recife researcher in Paris 13. That includes a 9-month sabbatical stay of Rios on an invited professorship, a few months sandwich PhD of Tabosa. I will come back. I'll come on this, and the thesis of Marco Soria in 91. What was the research topic that we developed between our two research labs? It was first, I mean, with Rios came 3 times. First time was to general visit in 83. Then we have a kind of important collaboration of phase conjugate laser and also Doppler free evanescence spectroscopy. And Daniel Bloch will talk about that, I think. And also instabilities. I will speak more about that. Fernando de Oliveira, which was assistant professor in Natal, came in the University of Paris North, but he stayed only 2 years. And he was purely theoretician and did not want to do any experiment in a way. And finally, after these 2 years, he went to Imperial College to work with Peter Knight, and he did very good job there. But it did not work very well. Seed came at the time we were developing saturated absorption and dispersion, and Tabosa spent 6 months in a sandwich thesis, and Marco Soria did his full thesis in Villetaneuse. The research topic here, I will develop that later. I would like to say that in the common publication, we have 2 coming from the work in Recife. And I would like first to show you that. It was the work with mainly the work of Tabosa and with Rios on the phase conjugation in statistics using CO2 lasers. And I remember that we have to make some improvement because we have a lot of problem with the noise in this experiment at the start. So I think coming at this point, I have to give at least a picture of both Tabosa, who already had some barb, some beard at that time, apparently, and Rios. I don't see the termite behind, but I think they are not very far. And since I am in the picture, I think a good picture is in Porto de Galinhas, where the 2 actors, I mean Rios and myself of the collaboration are with Claude Cohen-Tanucci and Sergio Rezende, will be called to more important position later. So I'm coming just to give you some work on what we did. I think what is interesting is instability using degenerate 4-wave mixing, because it's, I think, I'm not sure, but Rios may confirm, but I think it was the start of his interest in general laser instability, chaos, and stuff like that. So it started, in fact, by observing phase conjugate self-oscillation by degenerate four-way mixing in sodium vapor. And the reason is that you have, I don't know if you see at the top just the usual backward degenerate four-wave mixing geometry, where you have absorption of two photons from the pump, and you have emission of a probe photon and of phase conjugate photon. So you have an amplification of the probe and also emission on the phase conjugation. And if you are able to get efficiency which are larger than 100%, in fact, here we got 250%, then you can just suppress the probe and put a mirror inside, close to the medium, and then you get just self-oscillation. So we have that. We did that with Rios, and in fact, after we have a collaboration with Gilbert Grimbert and co-worker on the instability in general on mirrorless four-wave mixing oscillation, and that's this type of work. I mean, where we observe, in fact, that the oscillation is not exactly along the pump, but at some angle, which are determined by the nonlinear index of the vapor. It can be either in a ring or on a polygon. It's something which has had many development after. I mean, looking at these instabilities and this characteristic. That's I think it's important work that we did at that time between LKB, LPL, and Recife. So since we are chaired by Tabosa, I think I have to speak about the stay of Tabosa in Recife. And it was 6 months, and he did some work on optical spark splitting in non-degenerate wave mixing, and using two different beams. And you see that we are observing a very important stark splitting, which is in fact what we call usually the Hauter-Town splitting in radio frequency spectroscopy. But it was a nice work that has been done, and I think it was presented in the PhD thesis of Tabosa. And I come to a work that we did. We started mainly in 87, 90, which is a very important work because at least it started a research line inside the laser physics lab and also in other labs after about the world on looking at Van der Waals interaction between atom and surface as observed by selective reflection spectroscopy. I would like to remind you that what is the selective reflection? Selective reflection, you are sending a monochromatic light on the interface between a dielectric window and a vapor. And by looking at the selective reflection, you have an idea of what is the response of the atomic vapor close to the interface, because the change in the index is very close to the interface. And when we are using a vapor and a monochromatic light, and if you're at normal incidence, you are mainly sensitive, in fact, to atom moving parallel to the surface. And the reason is that the atom moving towards the surface are losing their excitation. The atom leaving the surface are starting from the ground state. So the atoms moving along the surface are not colliding with the surface, and they are giving a most important contribution. And when you are at normal incidence, it's mainly Doppler free for this reason. So, I mean, we have several stuff, which is a non-local response of the dipole polarization, and you have this logarithmic singularity for zero velocity with respect to the surface. And in the same time, you are probing a depth of the order of the wavelengths from the surface. So it's give you the way of probing atom in a Doppler-free manner close to the surface. And that was the main work of Marco Soria in Viltaneuse, and it observed the spectral observation by selective reflection, the surface-induced van der Waals attraction on atomic vapor. I would like to just to show you something where it's more clear. I mean, and that was the thesis work of Horacio Felach. Horacio Felach came from Montevideo. I will speak more after about the development of all this cooperation. And it was to use stepwise selective reflection and not direct selective reflection on the resonance line. I mean, you are bringing the atom in the resonance state, and then you are doing selective reflection on this transition. And what happens is that you have a channel of de-excitation of the upper level, which is resonant with the surface polariton of sapphire. And that means that you may have a resonant coupling between the surface polariton, if you have sapphire, which is close to the surface, and a de-excitation of the resonance state. So you have two resonators which are coupled, and we have coupled resonators. We know that we have a shift and broadening or stuff like that, and that's Horacio Felach observed, and I show you here the result. This is a spectrum of selective reflection at 876 nanometer on this transition, when for different windows, sapphire and YAG, and you see this is saturated absorption, which gives you the reference frequency, and you see that you have an important shift of the transition, which is directly related to the interaction between the atom and the sapphire surface, and this is resonant because of this presence of the sapphire surface sapphire polarity. And just to say, the first publication, it was published in Physical Review later after, but the first publication where we have Felach, I mean, Horacio coming from Montevideo, Rios was there at that time, and that we show, I mean, this redshift that you observe, which in fact is characteristic of a van der Waals repulsion, which is not so obvious from this, but when you make the calculation and you compare with theory, it corresponds to a clear repulsion. Okay, that was I would say the starting years, and I'd consider it's going from 1982 to 91, and after we have a kind of diversification in the collaboration, first in Brazil, because Marco Soria, after his thesis, and Martin Chevrolier went to Universidade Federal of Paraíba, João Pessoa. So we started a collaboration. We have many PhD together, PhD in co-tutelle between João Pessoa and Viltaneuse. I mean, I think to Thierry Passerat or Carlos Segundo. And in France, you have the collaboration also started with Institut Non-Hilaire de Nice in Nice. Robin Kayser should speak about that. But I think it was important because of the interest of Rios in leisure instability and chaos, and he was interacting a lot with Jorge Tredice, and concerning Jorge Tredice, at some time it was easier to see him in Recife than to see him in Nice. So I think he's following, and it's interesting because I remember going to the French consulate with Jorge Tredice, and I don't remember when it was, and Rios was supposed to come, but he came relatively late, and we enter in the scientific attaché office, and the scientific attaché, I think, thought that Jorge Tredice was Rios. So we have some interesting exchange at that time, and Rios appeared after. There was also extension to Laboratoire Coton, and Laurent will speak about that, and with Université of Angers, and Georges Boudet should speak about that, and Sid already spoke a little bit about this extension. In the international partner, we had the University of Republica. Sid explained the trajectory of Arturo going from a thèse of troisième cycle in France, in LKB, to a PhD in Recife, and after some postdoc and a short stay in PUC, he went back to Montevideo, Universidade de República, and we have a lot of collaboration with Lizama and Horacio, and in fact, it started in '91, and in '93 we have a ECOS collaboration between Montevideo and LPL, and also included at that time Gilbert Graber in the LKB. And in Russia, we have a three-party collaboration between Valsily Klimov and the Lebedev Physical Institute with Rios and us in LPL, and Daniel Bloch, I think, will speak about that. Okay, just to say, I spent I think 11 stay in Nordest. It's not bad because I went 13 times in Brazil, but most of the time it was in Nordeste, as you can see. And I would like just to say what Tabosa spoke about. It was a closing conference of the International Year of Physics, was organized in Recife in December 2005 with Rios, and I think I have a good picture where you have we have the two main people in the collaboration between Recife and Viltados, as well entouré by two Nobel Prize or future Nobel Prize. And at that time, Sergio was Minister of Science and Technology. In fact, Sergio Rezende came to France, into Paris in January 2005 for the opening of the International Year of Physics in UNESCO. But at that time, he was not minister, and after he became minister in the Lula's government. Okay, so I don't know. Yeah, okay. So I would like just now to speak about some recent research lines. They are not corresponding to a collaboration with Recife, because I have to say that the collaboration that I had personally with Recife was decreased in the starting of the year 2010, and in fact, the last time I went to Recife was in 2012 for the 40 years of the physics department of Recife. So I have a number of new idea of work which I developed either in Viltanos, also in Singapore, because I was visiting professor, part-time visiting professor in Nanyang Technological University in Singapore, starting in 2014. So I was interested in the optical pumping processes in electric quadrupole transition. In fact, it's connected to the work partly that we did with Vasily Klimov and Rios on the laser beam with optical with orbital angular momentum, because we show with Vasily Klimov and Rios and Daniel Bloch that usually, you know, when you are looking at electric dipole transition, I mean, there is no absorption of any orbital angular momentum. That's dipole electric rule. And when you are using a beam with the right, I would say, Lagergos beam or Bessel beam, we have the orbital angular momentum. If there is enough divergence of the field and magnetic field, you can have a transfer from the orbital angular momentum to the kinetic momentum of the internal kinetic momentum of the atom. And so you can observe that by using electric quadrupole transition. We also did some trajectory reflection on electric quadrupole transition. I started to be interested in interaction between atom and metamaterial using selective reflection, and the idea was to try to, I discussed with you the fact that the surface resonances, surface polaritons can have influence on the interaction between atom and metamaterial, and atom in surface in general, and metamaterial is a way of tuning surface resonances, and you can tune the surface resonances. I will show you that close to the atomic resonances. And in Viltanos, we have recently started, I mean, in the last few years, diffraction of slow metastable atom with a very well-defined velocity in material nanograting, and to look at the influence of Casimir-Polder interactions. And we have recently shown that even at a distance below 50 nanometers, because in material nanograting, the atoms are coming very close, you have to take into account the retardation effect in the Casimir-Polder interaction. I mean, you cannot just say that it's non-retarded. Okay, so I come to I will just present our work on atom metamaterial hybrid devices. The idea is to engineer metamaterial in order to tune the surface plasmon and make resonant the interaction between metamaterial and atom coupling. You can also expect atom enhancement of atomic width transition, because you have a strong field, but also a strong divergence of the field means that you can enhance electric quadrupole or magnetic dipole transition. And so it's a new platform for atom manipulation and trapping. So the idea is the following. I mean, we are using silver coating, 50 nanometer silver coating on which we are putting several array of slit, and this is done. By the way, this is done in in the Nanyang Technological University, in the Center for Nanophotonics, which has been founded by Zeludef in there, and which is very, very efficient. So they are able to make make some special type of, I would call metasurface because it's 50 nanometer thick, you see, and with different characteristic in terms of the holes that you are creating, and this, by changing the hole, you have different position of the surface plasmon, and you can see that you see here just the color is changing depending on the characteristic of the surface. And in fact, when you tune, when you change on the metasurface, going from one small system to another system, you change the transmission inside the metasurface, and you see that you can tune the surface plasmon from 700 to nanometer to 1 micron. So you can have, in this way, you can really see the influence of the surface plasmon on the atom. So we have done usual selective reflection experiment where you have a 852 nanometer laser, which is a narrow line width and tunable, which is sent onto a saturated absorption spectrum in order to have the exact position of this frequency and to tune it. That's using the usual saturated absorption setup with the cesium cell. And finally, we send that and look at the selective reflection on the a window, which is wedged with metamaterials. The metamaterials inside the cell. You have 18 cesium vapor. And we are looking at the selective reflection, and we are looking at the selective reflection as a function of the choice of the metasurface that we are doing on this metamaterial. So this shows you when you tune the surface plasmon, you see the difference in the selective reflection. This is just for dielectric surface, and for different surface with different wavelengths of the surface plasmon, you see a serious change in the position, and that is observed. Sorry, that is observed both in phase and in quadrature. And now to interpret that, you have to introduce Van der Waals coefficient, the C3, which is a characteristic of the interaction between atoms and surfaces, as a complex number. It means that we need to introduce, if we are not you suppose that C3 is real, you see that you don't have, that's a blue part. So the fit is not very good for both absorption and dispersion. And if you introduce a complex C3 number, that's for the black, you have a better fit. And in this way, you can measure both a real part of the van der Waals coefficient and the imaginary part. So you see that you have a kind of dispersion line shape for the real part when you tune the wavelength of the surface platform, and you have also an absorption part. This absorption part corresponds to a real tuning between the excited atoms in the resonance state and the metasurface. If the surface platform, I mean, was perfectly narrow and there was no ohmic loss, you can have a reverse process. I mean, the photon, which is absorbed by the metasurface, could come back to the atom. But in that case, we know that the line width of the surface platform is 20 of the order of 20 terahertz, is a lot larger than the atomic line width. So it's a kind of phanecoupling that we have, and it's a completely irreversible. I mean, the photon cannot come back. We interpret that by using a mean-field approximation for the 2D material here, where you do a mean-field approximation where you consider an effective surface material with varying dielectric constant as same far field property, but the surface placement wave doesn't appear only in the near field. When we do that, we get a kind of prediction which is supposing that the atom surface interaction is non-retarded, is purely van der Waals. You see that the dot stuff, and when you introduce a retarded transition, we get some difference, and that's compared to what the observation on the coupling between the silver metasurface and cesium. The general variation is okay, but you see that at least in the intensity we are not able to get. We get more in the resonance. It's more intense than it is in the prediction. Okay, I think I will finish the point. And I would like to say a few more, few stuff before finishing, that concerning the collaboration between the physics department of UFPE, and it was, we observed a very remarkable development in the year since 1983 in the activity of this department is remarkable, and it's increasing, and it's at the point where, in fact, some people researchers are leaving the physics department, the physics department, I mean, an optics component, to go to elsewhere. I mean, either in Recife, in Rio, or in I think to Claudio Lenz, or in Montevideo. So you have a development of the experimental physics which was quite important, and I would like to say that it was important because it's not always like that. It was real bilateral cooperation. It's not one side, because we have a noteworthy contribution coming from people from Recife and from UFPE, and that's with the term of new results, new ideas, and I think we'll have the opportunity in the following of the meeting to see all that. So to finish, I think I cannot leave without presenting the catamaran of Rios leaving for the race between Recife, leaving the Recife harbor for the race between Recife and Fernando de Noronha. It was in 2010, And you can be surprised that the bot is alone, but and you can consider that he's already in head, but it's not the case. It came 5 minutes after the others. Anyway, that's and another picture. I think that's for Saboza. I tried to persuade him that it's good to smoke Havana cigars. I think it was in 2008 or something like that, and he was pleased to do that. Okay, thank you very much. Okay.
Okay.
I had to stop
Thank
it.
you, Marcial. Thank you, Marcial. Your timing was perfect. So thank you for this nice and reviewing talk.
I don't know.
As I mentioned in the chat, if you have questions, you can raise your hand or ask directly in the chat. We have 3 minutes for questions if you have one.
Well,
Well,
maybe there will be other questions for the following. I mean,
okay. Anyway, the time is we are right on time. So
but it was a pleasure, and at least I can say that, to have this collaboration with Recife and the optics people in the department.
I should say that was a pleasure to us too, especially to me.
Barbosa, can I
Yes.
make a question?
Sure.
Can I raise a question? Not
Yes.
a question, but a comment. It's a long time that Marcial does not come to Recife. Next year, perhaps in August or September, we will have a LAUP conference here. So I would like to invite him to participate in this conference. We'll make a invitation letter sometime, but there is the possibility for you to come here August or September next year. I hope that the pandemic is finished at that time, so we'll have a conference with people present in here. So it would be very interesting for us if you could participate in this LAUP conference. That would be the second LAUP that you participate, right?
Yeah.
You came here for the first one.
Yes, I came for the first one. Yeah. Thank you very much, Sid. You know, I'm more free now in some way. So it's I'm not so busy.
It was a public invitation, so you cannot refuse it.
Yeah, he cannot refuse. Yeah.
Okay. So, yeah. Okay. So thank you, Marcial, again. And I think we should move to the next talk. And it will be presented by Professor André Mizirovich. Are you ready, André?
Can you hear me?
Yes, perfect. Okay.
So,
okay. No, let me introduce you first. Okay, let's see. Professor, first I would like to thank Professor Mizirovich for accepting our invitation, and I just want to say a few words about him. He told me that he pursued all his entire career at CNRS, at École Polytechnique in Palaiseau, and where he became a director de recherche, I should say in the highest level. And his main interest has been to study the optical properties of semiconductors, and recently the study of the filamentation process in various transparent media. And I think this says more than what I said. He has co-authored over 350 papers, and he has more than 25,000 quotations. So that's really impressive. So just a comment. I really would like to thank him because I think he really likes Brazil and the collaboration with Brazil, because he was the first one. I think the second day after I sent you the email inviting him, he promptly responded positively. So thank you, Andrea, for participating in this symposium. Okay, we can start now.
Okay, thank you very much for your kind introductory words. And I would like to thank the organizers to allow me to present this talk. And I would like also to express how much I enjoyed the several visits to Brazil, and I'm very fond of your beautiful country. So let me try now to share my slides. I don't know if can you see that or?
Not yet.
Not yet. Okay, I have first to partager l'écran, and then I have to do this. By the way, several times I had an interruption of, I hope it will not occur during my talk. So let me see how I can now share my slides.
Professor?
Yes.
Do you have your PowerPoint presentation open?
Yes, it is open.
Okay, so if you go to your Zoom window, you have a button. This say share screen at the bottom.
Yes, I share the screen.
Yeah.
Okay.
So.
Okay, I think.
Okay, so you can see your screen now. You just have to open your presentation.
Thank you,
Okay.
Bruno.
Can you see my presentation now?
Yes.
Okay. Okay, so I would like to speak about the process of filamentation of femtosecond laser pulses through transparent media. And the talk is organized as follows. I will first describe the general principle which allowed this process. And then I will shortly discuss some characteristics of these filaments. And I will finish with some applications. So if I send a short, intense laser pulse through a transparent medium, such as atmosphere, I expect normally during propagation that the peak intensity of the pulse decreases because of diffraction and because of group velocity dispersion. But in fact, if you do the experiment, you see the opposite effect. Here I show you one of the early experiments of filamentation. There was, down the hole there was a laser, a femtosecond laser with emitting pulses at 800 nanometers with a duration of about 100 femtoseconds and an energy per pulse of 10 millijoules. And if I look at the beam profile 50 meters later, what I see is an intense narrow spot in the center of the beam, and the intensity of this intense spot has been measured, and you can it reaches several times 10 to the 13th watt per square centimeters, which means that the intensity of the initial pulse has been increased by several orders of magnitudes. And I can, if I look further, you can see that this phenomenon of filamentation is very generic. For instance, here, changing the wavelengths, you can see that you have the same effect with a laser at 400 nanometer. And it is also quite spectacular in the range of propagation. Here, what I'm showing is a vertical propagation up in the sky of a laser beam with terawatt intensity. And you can see that this filamentary beam crosses a thin cloud layer, which is located 5 kilometers up in the atmosphere, and another cloud layer 20 kilometers in the atmosphere, and it goes even beyond. So it's a very spectacular effect. But on the other hand, you can also see it on a reduced scale. What I'm showing here is a piece of fused silica, 1 centimeter in thickness, and a pulse at 800 nanometer again is focused on the entrance of this piece of fused silica. And instead, you can see that instead of diffracting, the beam maintains in size and is propagated inside the sample. Of course, there is a scaling down of all the parameters to obtain this effect here. Instead of using a pulse with millijoules of energy, I only need a few microjoules of energy. So what is the origin of this effect? The first nonlinear effect which is responsible for that is the well-known optical Kerr effect, which states that the index of refraction of a medium, of a transparent medium, in the presence of an intense electromagnetic field is not a constant, but is changing. Usually it is increasing, and in first approximation, according to the law which is written here, it's increasing proportionally to the local intensity at time t. Now, if I have a beam with an intensity in the center of the beam, you can see that due to this change of refractive index, it will act as a self-lensing effect in the sense that here the index of refraction will be higher than on the wings, which is exactly the same effect as if you put a lens in the path of the wave. Except that this effect is cumulative. As you progress, you increase the intensity, which increases this optical Kerr effect, which leads to the catastrophic collapse after some distance. But eventually, the intensity of the pulse has grown so much that the molecules of air become ionized by a high field effect. And when they become ionized, then the plasma induce a change of the refractive index, which is negative. And this will act now as a diverging lens in the sense that in the center, this effect will be stronger than in the wing. So the dynamic competition between these two effects explain how a beam is stabilized with a narrow beam dimension over long distances. To solve this problem, one has to solve the nonlinear Schrödinger equation. Unfortunately, there are no analytic solutions. One has to solve it numerically. I will not go into the detail of all the effects which have to be included for that. I will just show you one example. This is a computation performed by Arnaud Couéron of an initial collimated pulse with a diameter of, shown here, this black curve represents the half width of the beam at half maximum. And initially, you have a first regime, which is ruled only by the optical Kerr effect. And you see that the diameter of the beam decreases first slowly and then very precipitously at some distance. And at that distance, the intensity becomes high enough that it ionizes the molecules of oxygen and nitrogen, and the defocusing effect prevents further collapse. And then you have formation of a plasma, a column of plasma approximately 1 meter long, which is followed by cyclic defocusing and focusing events, which become, as we progress, energy is lost every time you ionize the medium. And eventually these ionization spikes, which prevent the beam collapse, become more erratic. And eventually you have then long distances over which the beam maintains still a very high intensity, but just below the value necessary for ionization of the medium. And this explains why you can propagate with very little loss over very long distances. Now let me show you some self-actions which occur during this filament process. A first self-action is the pulse self-cleaning of the pulse time spatial profile. And I show you here two examples. One example is shown in a fused silica. What I show here is the exit shape, the spatial profile of the pump after crossing the 1 centimeter thick fused silica sample, with the sample and without the sample. And you can see that there is an improvement of the beam quality, similar to what you have if you send optical pulse in a fiber, in a guiding structure. The same effect is observed here in atmosphere. You can see an improvement of the beam quality as compared to what you have in the absence of filamentation. Now you can exploit this effect by using a configuration of degenerate four-wave mixing. What I'm showing here are two counter-propagating filamentary pulses which meet at a certain point, which is shown here. And then I send a probe beam which intersect this collision of two filaments. And this generates a signal beam which is counter-propagating and which I can analyze by putting a semi-transparent mirror on the pass. And what you can observe here is the entrance, the profile, the spatial profile of the entrance probe pulse, which is intentionally deformed. You see, it is and diaphragmed. And here I show you the beam profile of the reflected beam, which is considerably increased in quality. And this is due to the transfer of the quality of the beam profile in the filaments to the signal pulse. Another effect which is obtained here is that you can clean the front edge of the pulse. This is an important issue with very short pulses. When you want these short pulses to interact with a solid surface, you don't want to have light precursor, even at a low level, because they can modify the front surface, and the main pulse will interact no more with an abrupt surface, but with some diffuse surface. And here again, I show you the beam profile of the probe pulse, which has a significant background up to 10 to the minus 3 to 10 to the minus 4 as compared to the peak of the pulse before. And here I show you in red the shape of the signal pulse, where this precursor has been removed over 6 orders of magnitudes. Another effect which is occurring, another effect is the pulse time self-compression during filamentation. And the simulations show that an initial Gaussian pulse profile will deform during propagation in a complex manner, which is, sorry for this, which is shown here. And after some distance, there is the emergence of a single shorter pulse. This is the prediction. And experiments have been carried out in Zurich in collaboration with the group of Ursula Keller at ETH in Zurich. And what was done was to make two successive filamentations in two argon cell, first argon cell. Then we use chirp mirror to recompress the effect of the dispersion from the exit window, a second cell, and again, we compensate for the dispersion of the second window. And if you look at the pulse time profile, this is the initial pulse, 30 femtoseconds. After the first cell, we obtain 10 femtoseconds, and after the second pulse, you see 4.9 femtoseconds. Now, I would like now to mention applications one can do with filaments. There are many applications which often include the atmospheric science. For instance, you can use it to see the nature of a target at a distant target by LiDAR or by light-induced breakdown spectroscopy. There are some possibilities of obtaining a laser in the sky, but in this talk, I will talk about the possibility of triggering guided electric discharges and to use it to improve transport. And if time permits, I will also show you how we can obtain a virtual radio frequency antenna in air. So here is an example of two electrodes which are charged. And if I raise the voltage on this electrode, then I see a spontaneous discharge, which is usually initiated at some abrupt corner of the electrode. Now, if I let a filamentary pulse goes through this electrode, what I observe is that I obtain a guided discharge along the path of the filament, and an interesting effect is that the voltage necessary to obtain this discharge is reduced as compared to the self-discharge. Here is another example where a 4-meter-long guided discharge is obtained if you apply a voltage difference of 1 megavolt. Now you can make use of this effect to improve the speed of fast train. And the idea is the following. You generate a filament which connect two electrodes, and these electrons are supposed to represent the pantograph and the power line. And now we are going to do an experiment at a site where they probe the TGV fast trains, and we are going to apply the power supply which is equivalent to the power supply which is used for TGV trains in France. It's either a DC voltage of 4 kilovolts with a maximum current of 400 amperes, or it is a AC at 50 hertz with a 20 kilovolts voltage and a maximum current of 10 amperes. So we have a power supply in the range of the megawatts, in the megawatt range. And why are we interested in this? Because you probably know that what limits the speed of fast trains is first the mechanical friction between the pantograph and the power line, which increases fast at high speed. And also because at high speed, you generate oscillations of the power line, and they can decouple from the pantograph. And therefore, for instance, when they wanted to break the world record of speed with a TGV train, they had to stretch the power line intentionally over the distance of the trial in order to make this experiment. So with this scheme, what you do is you avoid any mechanical contact between pantograph and power line. And here I show you the experimental setup. We have brought the mobile terawatt laser system, which is contained in a container in the site of near Paris, where they test the TGV locomotives. Here I show you an example of the two electrodes which are connected by the filaments. And in the next slide, I show you the typical results. On the left side, this is the results obtained with DC voltage. So I apply the DC voltage here, and the pulse is arriving at that time here, at time t0. At time t0, the arrival of the laser pulse initiates a strong current passing through the two electrodes. And of course, you have to limit this current because of the very high electric power which is dissipated. You can do the same thing with AC voltage, and you can see once the laser pulse, the filament is arriving, connecting the two electrodes, you have an oscillatory current developing across the two electrodes. So, of course, this is not yet implemented in reality because femtosecond lasers are still fragile and difficult to align. And I would hate to sit on a train and suddenly being stopped and hear that, sorry, we have to realign the laser before we can proceed. But the concept is there. This is what is important, I believe. And in the future, one can expect more reliable femtosecond laser to develop. Second, I would like to mention that in the resistance in the plasma, which is generated, is low. It's on the order of 0.1 ohm per centimeter. And so the dissipative loss due to this connection is very low. It's a few percent of the total power which is injected. Now I want to discuss another possible application, and this corresponds to supersonic flights. Suppose when a vehicle moves in air at supersonic velocity, a shock wave is generated, and this leads to a considerable increase of the drag experienced by the vehicle. And this, of course, increases the fuel consumptions. Now, the common strategy to reduce this effect is to use a conical shape for the vehicle. But there are limits to what you can achieve in this way because of mechanical instabilities which develop if the spikes is too long, and also because the maneuverability of the vehicle becomes very low. So one idea is to inject a plasma in front of the vehicle, and it has been predicted by several authors that this should reduce the drag experienced by the vehicle. So we have done an experiment in a supersonic flow in Meudon on a small test model, which is shown here. This is it has this shape of shown here, and it is put in this chamber, and there is a max free flow of air flowing in this direction. This test model is mounted on a balance so that you can measure the drag it is experienced because of the airflow. And here you can see the plasma which is generated in front of the vehicle. Now I show you a result. Here, first I show you a Schlieren experiment which shows that there is a disturbance of the air pattern in the form of a lateral supersonic expansion of pressure, and resulting in a reduction of air pressure in the filamentary path. And this reduction of air pressure leads to a bubble in front of the vehicle of low pressure. And if you measure the drag, you see that there is a considerable reduction of the drag experienced by the vehicle. And this corresponds almost by a factor 2, in fact. In the experiments which were performed, the laser was at very low repetition rate, was at 10 Hertz, so that the average reduction of drag average over 1 second is negligible. So we are currently planning to perform a similar experiment, this time with a laser, a femtosecond laser, operating at 1 kilohertz. And the simulation predicts that in this case, one should have a steady improvement of the drag by 10 to 20%. So I hope we will get these results in the near future. So I think my time is up, and I would like to thank you for your attention. And if you have any question, please.
Thank you, Professor Mizirovich. So we do have time for one or two questions, so please you can either raise your hand or put the question in the chat.
Barbosa, I have a question.
Yes. Okay, please.
Okay. That's very interesting, this subject. We are performing some experiments in liquids, filaments in liquids. We don't have such high power laser that you have with 10 millijoules per pulse, but we have one with 1 millijoule. So we do some filaments. But then I have I was reading some of the papers that you published, and the papers that people try to interpret what's happened when you have this filament. And although I did not go deeper on that, I understood that there is some controversies in the literature, because some people describes the beginning of the filamentation by using the non-perturbative nonlinear optics. I mean, they speak in terms of high order susceptibilities. And I understood that other people say that that's not true.
Yeah.
Can you comment a little bit about that?
Yes, I think there are many. Yeah, there was indeed a controversy. Some people were saying, no, it is not the plasma which limits which prevents collapse of the beam, but higher order nonlinear optical effects. But there have been several experiments which show that indeed plasma is necessary, and plasma is in agreement with what is calculated. However, if you go to the far mid-infrared region, then the situation becomes different, because there you may very well have other nonlinear effects, such as high harmonic generation, which acts efficiently to reduce the collapse of the laser. And so plasma in this case plays a less important role. This is an interesting new development in the field of filamentation, but it requires very powerful lasers for a study in air, which are currently not often available. But I think if you are in the near infrared or the visible, the traditional filamentation picture, which I described briefly in the introduction, is valid. There is no doubt about it.
And I have a second question. Tabosa, is it okay or not?
Yeah, in principle, Robin is, if it's very quick, then you can ask, but there is another question that...
okay, so let's, Robin.
Okay, thank you. You can discuss it.
My question is very simple. My question is very simple. Are these filaments that you produce, can you say that those behaves like solitons, partial solitons?
Again, it's a good question. If you do the experiments in a few silica, if you do it in the normal dispersion region, the situation is complex. You have to, you don't have solitons. However, if you go in the anomalous dispersion region, the pictures become strongly simplified, and you have something which is akin to a soliton, in the sense that the pulse keeps its shape both in the time and space over the propagation. So dispersion, the role of dispersion is group velocity dispersion is very important.
So it's a kind of light bullet.
It is similar to what happens in optical fibers. If you want to have a soliton in an optical fiber, you have to be in an anomalous dispersion region of the fiber.
Okay, thank you very much.
Okay, now you, Roman, please.
Yeah, okay, can you hear me?
Yeah.
Can you hear me? Yeah. Can you, yeah, you hear me? Yes?
Yes.
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 Okay. Yeah. So really impressive work, in particular the creativity of what comes out of this nonlinear optics. It's just amazing how creative this field can become. It's really, I'm really impressed. So my question concerns the connection to, there's a growing field now which is called quantum fluids of light, which makes very similar experiments of what you do, but they call it different names, including me, but okay, so if they call different names. So one particular interest nowadays is, so I have two questions. The first one is, you work basically at 800 nanometers, if I understand correctly. Can you exploit resonances in oxygen and nitrogen? Are there any molecular resonances? And could you tune from the focusing to the defocusing regime by changing the frequency, the mean frequency of the light?
Well, yes. There is a strong interest currently in trying to obtain air lasing with filaments. And it turns out that if you use laser at 800 nanometers, you have a quasi-resonance between in the singly ionized molecules of nitrogen. And this helps, we believe at least, it's a subject which is still a bit controversial, but we believe this allows to obtain a strong amplification in the absence of population inversion. So I think it's a very interesting resonant effect. You have a coupling, a V-coupling, which allows this effect.
It involves an ionized state.
Yes, you have a transition which is between the second excited state of the ionized molecule and the ground state of the ionized molecule, but there is an intermediate state which is resonant with the pump, and this forms a V scheme and allows amplification in the absence of population inversion.
Okay. And yeah, just to comment on this discussion, are there solitons in the community of quantum fluids of light? They would ask you, do you have droplets, light droplets? Because there's a compromise between a repulsive and an attractive part in the edges of the wave function, let's say, and they call this droplets now. So do you have droplets of light? Or so it's a little bit the different physics from the solitons, because the eigenfunction has different shapes. But so maybe you have also droplets of light, not only bullets of light, but droplets.
Maybe when you have these sporadic cycle-decycle pulses, maybe you can call that droplets. I don't know. I never thought of that. But
do you see arrays, self-ordering? Do you
Sorry?
see arrays? Do you see spatial ordering, like period?
Oh yeah, you can organize. Well, you can get many filaments in parallel, and you can organize them by putting mask or playing on the face of the initial pulse. Yes, you can.
It's not self-organized. It's not self-organized. It is not self-organized.
They self-organize. Yes, they self-organize. For instance, if you put an aperture, then they will tend to organize on the ring, on a ring structure. Yes.
Okay. I will not abuse my time. Okay. Thank you very much.
Okay. Thank you, Professor Mizirovic. I think we should move to the next talk, which will be presented by Professor Arturo Lezama, which who I'm really glad to introduce here. So Arturo Lezama is a full professor at the... Okay, can you hear me?
Yes, yes.
He's a full professor at the Universidade de la Republica-Uruguay, and I would like to say that Arturo is a very bright scientist, which has greatly contributed to the development of physics in his country. And he's now leading a group developing research in the frontier of quantum. Very, very, very productive and interesting research. Arturo also has an interesting history of in the context of the France-Recife Collaboration, because after completing his undergraduate studies, I think he mentioned in his talk, he decided to move against the natural flow and then moved to, from Paris to Recife, where he received his PhD. So as a student, he had the unique experience of doing physics under very different conditions. So I think he also mentioned along his talk. So it's a pleasure, Arturo, to have you here. So please have the screen.
Well, Tabosa, thank you very much for your kind words. Are you seeing this? Are you seeing the presentation?
Yes.
Okay. So, well, at first I must say that I was really touched and very pleased by your invitation to participate in this symposium. As, of course, I am not French nor Brazilian myself, so one can wonder why I was invited. But as you already heard, I had the luck to be a very privileged witness of the initial stages of this collaboration and to have to participate in that collaboration. And since then, this collaboration has been very fruitful for my personal research, but also for the development of physics in my own country. And there is, I would say, some sort of triangular collaboration that is very rich and that has been very fruitful for us. So this is what I am going to present today. I will say a few words of personal experience, but not too much. And then I will just mention some of the topics that we have been addressing in recent times, and each of which has some motivation or some very strong input coming from the collaboration either with French colleagues or Brazilian colleagues. Okay, so talking about personal experience, I was listening earlier to Martial's talk where he mentioned some strange sighting in the UFPE campus where, for instance, they saw some cows in the campus. And then I couldn't resist mentioning one of my personal experiences in the subject. So this was an evening, late evening. We were leaving the department. It was a rainy day. And we were just a couple of colleagues, including Tabosa, waiting for the car that was going to bring us home. And so at some point, Tabosa, with no special emotion in his voice and very naturally, told me, "Be careful behind you." So I turned around and I saw this, a walking fish. So this, I doubt that anyone has ever seen anything stranger in the UFPE campus, or by the way, in any other campus around the world. This was a walking fish, very alive, and just moving around in the parking lot. So this is really something very strange, and I cannot forget about this scene. And also I cannot forget how natural it was for Tabosa to see a walking fish. Okay, so now I go into more serious business. And of course, thanks to our collaboration with France and with Brazil, we started a new lab in Uruguay, and the initial laboratory, which is a laboratory of radiation matter interaction and atomic physics interaction, started with the building of a magneto-optical trap. By the way, this magneto-optical trap was granted with a European project that included Martial Duclois and Gilbert Grambert as participants, and it was very important for the creation of our lab. So this picture is not from that time. This is a very much recent picture about a new cold atom setup that we have we are mounting nowadays. And I am very, very happy with the improvement, with the progress of this field. So here I have a small, sorry, I see some problem here. Well, it does. I am sorry, it doesn't work. It was supposed to be a video of the atoms moving in a conveyor belt, and the conveyor and the atoms were moving around some 2 centimeters and coming back to the original position. And this is part of the some proposals that we are going to develop in the near future. So I come back to my presentation. So this is something that we are working on at present, but I would like to review some previous topics. So one of the subjects that we have been addressing is the study of atoms in confined situations. More specifically, we have worked with atomic vapor that are contained within the porous of a porous dielectric transparent medium. So the medium that we are talking is just ground glass contained in a glass tube, and the glass is compacted, and within the grains of glass there are some rubidium vapor, and we have been working on the spectroscopy of this system. So this system, it can be very challenging because there are lots of disorder. The porous, the grain size are random, the geometry is completely random, the atoms are moving, and the light propagation is random as well. I must say that this subject is again originated in the collaboration with our French colleagues, because the study of atoms under confinement is a subject that is dear to Daniel Bloch and Martial Duclois, and they are at the origin of these ideas. So here I just show some example of how strange the spectroscopy can be in this system. In the upper picture, what we show is the transmission through the sample. I mean, just collecting some light at the side of the sample, while we scan the frequency of a laser that is illuminating the sample. And we see that the transmission is rather flat, in spite of the fact that the laser is tuning around the absorption lines of the rubidium D transitions. And the fact that the transmission is flat is not because there is no absorption. It is due to the fact that, in fact, there is absorption, but since the light propagation is completely random, it is not possible to distinguish photons coming straight from the laser than from photons that can be emitted by the atoms. So since the atoms are absorbing and re-emitting light, there is some sort of compensation, and you cannot see the absorption directly on the transmission. But if the absorption is present, and this can be proved by studying the transient behavior of the light. So what we do is that we did was just to turn off suddenly the laser excitation. If you are off resonant, this means that the transmitted light is going to decay immediately. But on resonant, there is a longer delay for the decay, and this is just due to the excited state lifetime. So by studying this transient, it is possible to address the role of the absorption and the role of the fluorescence, and prove that fluorescence is indeed present, absorption is present, fluorescence is present, but the two compensate each other. And something interesting also occurs if the density of the atomic medium is increased, but because when the density is sufficiently large, photons have the opportunity for being absorbed and re-emitted several times by different atoms. And this increases the likelihood for the unexcited state to hit the wall of some poros and decay non-radiatively. So under such conditions, the balance between absorption and emission is lost, and there is some visible absorption line in the transmission spectrum. So this is just very simple physics concerning linear atomic light interaction, but we can see more complicated features if we study some nonlinear effect. For instance, here we have studied two photon excitations of rubidium into the 5D levels. The two photon excitation is achieved by two infrared photons, and from the 5D levels, the rubidium can decay, emitting some blue light. So we have been recording the intensity of the blue light as a function of the frequency of one of the two infrared lasers while keeping the other one fixed. And we observe very strange and unusual shapes for the excitation spectrum with these flat tops. And the flat tops, observed here or here, they can be well reproduced in theory, and they are a consequence of the random nature of the light propagation in the sample. Due to the random nature of the light propagation, direct absorption, two photon absorption from the ground to the excited state is not possible, because it's not possible to keep phase matching. So the only efficient mechanism is the stepwise excitation, first to the intermediate state and then to the upper state. And the two photon resonant condition for the stepwise excitation is dependent on the atomic velocity. And in our medium, there are lots of moving atoms. The light is coming from every direction because of the random propagation of light. And one can show that the two photon resonant condition, if one of the lasers is kept fixed but with some detuning, for the other laser, there are within some interval, the two photon resonant condition can always be achieved by some choice of the angles between the propagation wave vectors of the fields. And since the medium is completely random, there are always some wave vectors achieving the resonance condition, and this is the reason why we observe this very strange resonance line shapes. Okay, this is just some illustration of nonlinear optics in this medium. This can eventually give rise to some possible spectroscopic application. For instance, here we have shown that if we just collect some retro-reflected light in a random direction, and while illuminating our sample with resonant light, we can observe some subdoppler features. And these subdoppler features can be explained like just a saturation absorption process occurring at the entrance of the disordered medium, not inside the bulk, but at the entrance, because there is some incoming light with some relatively well-defined wave vector, and there is some retro-reflected light produced by the scattering of the disordered medium. And in the real direction, then we have the well-known saturation absorption effect. And what is interesting about this system is that it is alignment free. I mean, you can just put your sample in any position and send the light approximately perpendicular to the surface, but not so too much, and collect the light in any backward direction, and you will still be observing this narrow resonance that can show that this can lead to some possible application as a reference cell. Okay, so to end up with this subject, I would like to mention what we are working on now, which is a subject which is dear to Robert Kaiser, among others, which is the coherent backscattering, also known as weak localization. And what we do here, we have been done is just, we have our random porous meat sample. We send some light on the on the sample along a given direction, and we study how much light is backscattered at an angle theta with respect to the initial incident direction. And the coherent backscattering effect, which is a well-known effect, is a consequence of the fact that two counter-propagating diffusing paths have exactly the same length. In consequence, they interfere coherently and they interfere constructively exactly in the backward direction, and there is a decay of the constructive interference as a function of the angle theta. So we can observe this very nice retroreflecting coherent backscattering cones, and the observation of these cones, it can be a very precise and useful tool to characterize the mean free path of the light in the random medium. And in this particular sample that I am showing here, this was about 30 micrometers, which is not very far from the size of the grains, the glass grains that make our system. Okay, this is ongoing work. We are planning to introduce the atomic vapor within the porous medium. So we expect this line shape to be modified somehow by the presence of the atomic vapor when the vapor is near or at resonance, and we want to study this modification. Okay, so much about this subject. Then another subject that we have been working is the production of some non-classical light. More specifically, we have been working with squeezed light. And we obtain squeezed light using atomic physics, probably by the simplest means to produce squeezing, which is just to send some linearly polarized light across an atomic vapor sample. And due to the nonlinearity, the nonlinear interaction between the light and the atomic vapor, the orthogonal polarization, which is just the vacuum at the entrance of the atomic medium, it is after the atomic medium is squeezed. So we have squeezed vacuum in one polarization, and we have the strong linear polarization on the orthogonal polarization. So since we are talking here about quadrature squeezing, we need to implement for the observation this setup, which is the usual balanced homodyne detection setup, where the strong field, the strong polarization component is used as a local oscillator, and it is mixed in a beam splitter with the vacuum squeezed field. And the difference is recorded here, and this is the usual homodyne balance detection signal corresponding to the detection of a quadrature. This scheme is, of course, relatively straightforward, but it's not as simple as it looks, in the sense that, for instance, if one wants to produce a picture like this, where the maximally obtained squeezing is recorded as a function of the laser frequency, here in this scale, 0 means the shot noise or the vacuum field fluctuations, and below 0 means that we obtain some squeezing. In order to obtain a picture like this, one has to keep track of the quadrature that produces the minimum, the maximum squeezing. And this is not easy and normally involves some relatively sophisticated tracking setup. Okay, our contribution to this field is relatively straightforward, and it comes from the fact that when we look at this setup here, we realize that all we are doing here is just playing with polarization. We are separating orthogonal polarization, introducing some wave plates, some retardation, and recombining the polarization again. So this is just a game with polarization. We are just detecting here the intensity difference between two orthogonal polarization, which means that in fact we are observing a polarization squeezing, and that the observable that we are looking at is oh, sorry, this picture is not good. It's nothing else than a Stokes operator. The way we are observing here is a Stokes operator. So by this simple realization, we can simplify a lot the detection setup, in the sense that there is no need for separation of the beams, and no interferometer and no instabilities, and then this can allow us to obtain a very large, to improve the detection of squeezing, and we are the holders, we believe, of some world record, something like 3 dB of squeezing in this system. Okay, the fact that we can think of this effect like a polarization squeezing can also be improved by the consideration that the state of the field is a Gaussian state. So if you have a Gaussian state, all the information that can be obtained from this state is contained in the covariance matrix, which is just the fluctuations for different combination of the quadrature. And if you can have the covariance matrix, you have all the required information. And we can address the covariance matrix just by considering 4 different positions of one of the wave plates included in the setup. So just by 4 measurements, for each laser detuning, we have the corresponding covariance matrix, and then with the covariance matrix, we can do whatever we want. For instance, plot the maximally obtained squeezing as a function of frequency without any need of any sophisticated electronics or something like that. So this is a very simple means of measuring squeezing and at the same time manipulating the information just with the use of the covariance matrix. So we have tried to make some use of this information, of this possibility. And one game that we have been playing is that we can produce entangled light just by combining on a beam splitter the squeezed light that we can obtain with our atomic system. So we put our beam splitter and we send the light to 2 different positions, Alice's lab, Bob's lab, and we can check that there is entanglement between the 2 systems. And indeed, that can be done because we can have access to the complete covariance matrix of the 2-mode system, and just with some mathematical manipulation, confirm that there is entanglement between Alice and Bob. And this is plotted in this picture where we have some of the quantifiers for entanglement, like for instance, the minimum partial transpose eigenvalue, and there is entanglement when this value is below 1, or the logarithmic negativity, which is shown in blue, and there is entanglement when this value is above 0. So, okay, we observe the entanglement, we observe, and we have made some some attempts to observe steering. Steering is another possible correlation between the 2 systems, where Alice can somehow modify the statistics of Bob's measurements by just choosing what to measure on her side. So these crosses here show an attempt to observe steering. We didn't see any steering at the time, and so that made us to consider more in depth what are the difficulties for obtaining steering. And the difficulty comes essentially from the fact that the states that we produce in our system are not pure. There is a lot of excess noise that can be seen, for instance, in this picture. This is the squeezed quadrature. It goes below 0 by 2 dB, but the anti-squeezed quadrature goes above 0, but much more than 2 dB. So there is a lot of excess noise, and the states are therefore not pure. So we have been addressing the conditions for the observation of steering in the presence of not pure states, and this is a theoretical work that have shown that if you have some squeezing, then you may require some purity for observed steering. But a very interesting result is that, for instance, in the case of the 50% beam splitter, if you are able to squeeze the light to 30%, to 1/3 of the vacuum fluctuation, then the state is going to be steerable no matter how big the excess noise is. So this is an interesting result. However, the requirement on the squeezing is relatively strong, as 30%, which is not achieved in our system. However, this requirement is less strong if the beam splitter is not 50/50, but for instance, if most of the light goes to Alice, then just with 50% squeezing, we should be able to observe steering, but 50% still is at the limit of what we can achieve in our system. So, okay, we couldn't observe steering so far. Okay, just to finish with this topic of squeezing, we would like to investigate more in depth the origin of the squeezing process. So in the past, we have done some numerical work that shows relatively good agreement between the experimental observation of squeezing and some theoretical prediction. But these theoretical predictions are kind of black box ones where we solve the Heisenberg-Langevin Maxwell equations, and we take into the consideration the Doppler effect due to the fact that we have a hot vapor sample. So the prediction relies on some relatively involved structures for the individual velocity classes. And for instance, for the zero velocity classes, this is what the squeezing spectrum should look like. So we would like pretty much to observe this structure, and we are working on that. But the point is that this needs to be done with cold atoms. And if you shine strong light on cold atoms, most of the time you are going to destroy your system. So what we are attempting at the present moment is to do this experiment with a cold atomic cloud and send linearly polarized light from opposite sides in order to try to counterbalance the mechanical effect of the light on the atoms. And we are going to look into the transmitted light in the opposite in the orthogonal polarization, and we expect to see some non-classical correlations appearing between the two detectors due to the four-photon process where two strong linearly polarized photons are absorbed and two correlated photons are emitted in the orthogonal polarization and in opposite direction. So this is currently underway. It's not an easy experiment, and this is one of the reasons why we have developed the new cold atom experimental setup. Okay, so let me now mention some of our plans for the future. And our plans for the future is sketched in this transparency, where the idea is to put atoms near some dielectric resonators. So the dielectric resonators are these small cylinders of some material that has a relatively large dielectric susceptibility, and these cylinders of material can sustain electromagnetic modes, for instance, whispering gallery modes that are contained in the around the volume of the dielectric. So these whispering gallery modes can have a relatively large Q factor of the order of several thousands, and they are mainly contained within the ceramics, but they also have some some evanescent wave leaking out outside, evanescent wave outside the dielectric, and our idea is to put some cold atoms near this resonator. This is, as you see, this is sort of a cavity QED experiment that, of course, has a long history. The resonances of this dielectric resonator lie in the tens of gigahertz range, which are exactly the resonant transition for Rydberg atoms if the initial and final states are properly chosen. So what we would like to do is to approach some atomic cloud to the resonator, promotes possibly just one atom into a Rydberg state. And I mean one atom because we will be affected by the Rydberg blockade effect that only will prevent more than one atom to be excited, and approach this Rydberg atom, excited Rydberg superatom to the dielectric, and hopefully observe some coupling between the atomic transition and the dielectric resonance. This is some version of the atom surface interaction that has been studied so much by Martial and Daniel and Horacio Failacci, my colleague, who is participating in this experiment. Okay, so this is for the future. We are doing good progress in this direction. This is the scheme of the experimental setup. This is our vacuum chamber, and here is going. The red cylinders represent the crossing beams for the magneto-optical trap. The green line represents the conveyor belt laser that's going to move the atoms around, and we would like to move the atoms from the center of the moat to near the dielectric cylinder, which is represented here in yellow, and we are going to try to observe the interaction between Rydberg atoms and the dielectric resonators. We have also planned for some electrodes to be able to ionize the Rydberg atoms and collect them. They collect the ion with some channeltron, and so have access to some sensitive detection. Okay, so this is what we are mainly working at present, and as there are, of course, lots of challenges that we will have to face, and we hope that we can collaborate with our friends in Brazil and in France along these research lines. Okay, just to finish, I would like to just present a list of some of the many Brazilian, French, and Uruguayan persons that have been participating in our work. On the French side, I just mentioned these 5 persons because they are probably the most representatives of our collaborators, but I am sure I am forgetting a lot, many more. The same for Brazil, in the case of Brazil. And this is our team here in Uruguay. I would like to mention especially Horacio Failacci, my colleague who has been participating since the beginning in all these adventures. And Juan Andres Muniz, which is working with us since 2 years ago, and he has done a really fantastic job in the implementation of the new cold atom chamber and participating in other experiments. So Adriana Aujanet also has some personal history of collaboration with Brazil that probably some of you know. And I must say that I included in this side of the picture Sergio Barreiro, who in fact is not longer in Uruguay. He is at present in Recife, but he has always been considered some emeritus member of our team. Okay, so with that, I thank you very much again for this opportunity. It was very nice to be present in this celebration, and I would also like to congratulate the Department of Physics of the UFPE for its very successful first 50 years of work. Okay, thank you.
Thank you, Arturo, for this impressive talk. It's really amazing the amount of interesting new results that you presented. So the section is open for questions. We're a little bit delayed, but we have time for one quick question you have. Robin, your microphone, Robin, I think. Your microphone.
Okay.
Your microphone.
Okay, no, it's okay. Yeah, okay. Now you hear me?
Yeah.
Can you hear me?
Yes.
Yes. Okay, now just a quick question. Do you know the origin of the excess noise in your experiment? Is this from the lasers, from the atomic side, or where's the excess noise coming from?
The excess noise is mainly coming from the atoms. I mean, at the same time that we have this 4-photon process that absorbs 2 photons and emit 2 correlated photons, there are other processes like spontaneous Raman scattering or things like that that produce noise at the same frequency and probably are unavoidable, probably. And but we guess that this is the origin. But we would like to check all that. I mean, we have this intuitive idea, this numerical simulation that seems to be correct, but we would like to check that on real pure a real pure cold atom sample.
No, but because if the noise comes from the internal structure of the atoms, even cold atoms will probably keep this spontaneous Raman channel.
I am afraid so, yes.
Okay. Thank you.
Okay, thank you.
Okay, any other question? Okay, if not, as we are delayed by about 10 minutes, so I propose for the second part of this symposium, we should come back at 12:25. Okay, so we have 20 minutes for a coffee break or whatever. Okay, see you in 20 minutes. Bruna, você me escuta? Alô, Martina.
Oi, Tabosa. Estou aqui. Oui, oui, j'ai vu. I'm ready.
Tá tudo certo?
Certíssimo.
Ótimo. Okay. I think it's time to restart the symposium. We will start the second part with the talk by Martine Chevrolier, our next speaker. Martine Chevrolier is a full professor at Federal Rural University de Pernambuco, here in Recife. And she is actually the director or the coordinator of the graduate program in applied physics here at Rural University. Martina, as her name suggests, was born in France and received her PhD from Université Paris-Nord, I think in 1990. And since 1992, she moved to Brazil, and after spending some period at the Federal University of Paraíba, she took her actual position in 2015 in campus de Santo Agostinho. Martina's main research is dedicated to the investigation of atom-surface interaction, where her group has done many original and important contributions. So I would like to thank Martina for accepting our invitation, and I'm sure we all will enjoy her talk. So please, Martine, have the screen.
Okay, so Tabosa, thank you for your kind introduction. I think this one. Okay, so a few corrections. I had my PhD in '92, and another detail: Georges Boudebs has left the room, but I was born in Angers, although my scientific career is not linked to this town. So I want to thank the organizers for this invitation to this nice symposium. I will talk on the behalf of also on Marco Zoria. Our trajectory, as you will see, is closely linked. And we are currently at an engineering school of the Federal Rural University of Pernambuco, and it is located in a town.
Martina, excuse me.
Yes.
Can you speak a little bit louder? I cannot hear you very well. I'm not sure if the problem is with me.
Okay. Okay. Maybe I can. Yes, I have some problem with my. Is it better?
No, not really. Well, I can hear, but not.
Okay, I know my microphone is not that good. I tried yesterday to regulate it, but let's see if I can.
Maybe it's a little bit better now.
Okay, so I will try to speak louder, but I am not able to change the settings of my, okay, on the Zoom, unfortunately. I think it's my computer. Okay, so we are currently, okay, let me share again. Am I sharing? I am, yes. Yes, we are currently in the this new campus of the Federal Rural University of Pernambuco, which is located in Cabo de Santo Agostinho in the south of Recife, a few 30 kilometers south of Recife. So I will speak today really a very superficial overview of our trajectory on three main lines of research. The first two are strongly motivated, and we had interactions with groups in France, the study of atom surface interactions and of propagation and diffusion of light in resonant media. The third one is more limited to our group in Brazil, but who knows, we can have some collaborations, and this is a field where we are currently working a lot. So both Marco Zoria and I, we had our PhD degree in France, in the LPL in Paris North, under the supervision of Martial Ducroix and Daniel Bloch. And the line research during this PhD was the study of van der Waals attraction with between atoms and dielectric surfaces using this technique Martial has spoken of, which is the selective refraction. And so we were able at this time to experimentally observe, okay, the effect of these interactions on the line shapes of the reflected beams, and we were able to deduce the C3 coefficient on the first and second resonance of the cesium on two different substrates, glass and sapphire. So once we settled in Brazil, which was in 94, okay, we went to João Pessoa at the Federal University of Paraíba, and we went on this subject of studying surface interaction with various techniques, okay? So this first example here, with still a collaboration with the team in Villetaneuse, Daniel Bloch, Michel Fichet, and Martial Ducroix, still the selective refraction, but at an interface with a metallic layer. This is a student, undergraduate student from our group who participated in this work. And here another technique, which is a reflection spectroscopy with evanescent waves in a probe pump-prone configuration to infer some surface effects. And okay, so this kind of spectroscopy we were doing at the time. Here we have a very recent collaboration with the group of Daniel Bloch and Athanasios Laliotis in Villetaneuse to 2017. This is the observation, this time with a very different technique. We detect the fluorescence detected backward by an excited hot vapor of cesium. And there is a very narrow, okay, subdoppler contribution here, which is due to the interactions of the cesium atoms with the surface. Okay, so you have to have quenching effect on the surface and a very small depth of interaction. And so this is a work. I want to emphasize here that we are, the both of us, myself and Marco Zoria, Daniel Bloch and Athanasios from the lab in Paris. And this student, Jean Carlos, was doing its PhD at the time in their lab in France, but was a former student of us, a master student. All, and I didn't mention everything, all these experiments were in the classical description of adsorption interactions between surfaces in atoms in terms of thermodynamics parameters like absorption energy and absorption times, etc. But our quest has been during a long time to observe the effect of the quantization of energy of the atom in the surface well. And for that, so we wanted to see the effect of these bound levels. And for that, we needed cold atoms. So we first carried out a series of theoretical studies to infer important parameters such as the level spacing and also the transition probabilities. And we used a scheme of atom surface photoassociation in the same way that you have atom-atom photoassociation to form molecules and eventually long-range molecules. And so experimentally, we made a first magneto-optical trap at the beginning when we were in Brazil. And we made it at the center of the cell, and we approached the surface of the cell from our trap, and we looked at the fluorescence of the trap and of its reflection in the window. And we can see that with the limit of resolution of our camera at this time, okay, there are atoms which are close to the surface, but there was very few atoms left. The density was not sufficient. We attributed it to the fact that here, let me show you, the surface cuts the capture volume in the atomic trap and in the magneto-optical trap. And so we built in João Pessoa a special cell, João Pessoa UFPE, a special cell, okay, where we had this, I don't know, is it very clear here? We have a configuration of trapping beams, which is not really perturbed by the tip. This is a crystalline tip, okay, here. And it allows, this tip allows for the incidence and the reflection of a probe beam, okay, to probe the interactions of the atoms with the surface. It happens that we had a lot of problems with the stability of our magneto-optical trap, and due to the fact we were going to the United States at the time, and we stopped these experiments. And when we came back, this was this very interesting publication by this group, Afanasieff and Balikin, which attributed a phenomenon, which I will explain, a phenomenon observed in a thermal vapor to quantum absorption. So we were very interested, and we decided to investigate this phenomenon. Okay, so let me show you here. What is the phenomenon? It is the fact that when you have a cesium vapor cell, like the one we use, and if you illuminate the interface between the window of the cell and the hot cesium vapor, okay, you can observe the formation of a metallic film at this interface, depending on the conditions of atomic density and essentially Windows temperature. So we decided to investigate this, and thus we have pictures of our films. Okay, so we have the formation of the film at the surface, and the thickness profile of the film follows the transverse intensity of the current laser beam. We have tried it with a few very simple beam profiles, okay, Gaussian, donut, and asymmetric Gaussian. And I won't enter into the details, but with a probe laser, we probed the growing of the film at this interface here, and we measured as a function of the atomic density, and it was linear. So it's a problem who doesn't involve collisions. And we also measured as a function of the intensity of the pump laser, and it has a variation. It is very cubically with the intensity, and quadratically when at resonance. So rapidly, the interpretation is that it is the ionization by 3 photons, okay, on one atom, and these ions, okay, cesium ions, they will begin growing a film or not, depending on the state of the surface before the pump laser is turned on, if the cesium coverage is low. And this depends on the relative values of the adsorption, which is linked to the atomic density, and the desorption, which is linked to the temperature of the surface. If the cesium coverage is low, you will have the formation of an electrical double barrier, where the positive part of this barrier points towards the inside the cell and will repel the cesium ions. But in the case we have a high cesium coverage before, okay, turning on the laser, this lowers the substrate work function and will allow for the neutralization and adsorption of the atoms. So this is a work we are very proud of, okay, a very nice laser induced surface effect. Okay, it's not very observed because you have to be in certain, it's a very slow process, free photons, sorry. And so, and also it requires some high density. And so this is the publication, and another one, a follow-up of this first one. So this is only in our group in João Pessoa, but these names will appear after, okay, Wellington, Thierry. This experiment here, I want to talk, it's also an experiment on studying atom surface interactions. In this case, we were detecting the fluorescence from two cells which differ only in the states of their internal walls. Okay, this cell has is bare glass, okay, inside, and this one has a coating of sealant film, which is meant to decrease the collision time of atoms with the cell walls. And so you can see here the same configuration, geometrical, excitation, everything, but you see that the fluorescence is very different due to the surface state. And so by measuring this, we treated the radiation trapping, which is the multiple scattering of light, okay, inside this volume. The laser is here, and we treated this radiation trapping here as a normal diffusion process of photons with a defined mean free path and diffusion coefficient. And we published this paper, so we were able to deduce some information about this state, surface state. And this was when Robin Kaiser drew our attention to the fact that it was already known that superdiffusion was known to occur in hot atomic vapors. And so it was the opportunity to a collaboration which resulted, okay, here I will show superdiffusion. And so we thought, okay, we treated our radiation trapping this way, normal diffusion, and this is superdiffusion, okay, Levy flights. And so this was the opportunity for a nice collaboration, which resulted in this paper, okay, where the fundamental ingredient leading to superdiffusion has been observed experimentally in Nice and numerically, okay. Então, there has been some follow-ups here with this team, Nicolas Mercadier, William Guérin, Robin, etc. And so this was our departure from the study of atom surface interactions, actually, because we began studying processes of propagation and diffusion of light in resonant atomic vapors. And I have not mentioned other works we have done on this subject. I just want to speak here of what we are doing now. Okay, we are studying the propagation of spatially incoherent fields in a nonlinear medium. It means we are exploring the strong non-linearities, okay, of here we have alkali vapor, and we study we want to see how the correlation induced by the non-linearities in the cell will affect, okay, the statistical properties of especially incoherent field, okay, in this medium. Specifically, we have a speckled pattern, okay. We create here, for example, with a diffuser, we have a laser beam, a diffuser, and we make sure that at the entry of the cell, this pattern has a normal distribution, okay. So this is a normal distribution of fields, and this is here the distribution of intensity. And we see, so this is the intensity, this is the intensity correlation. So at the entry of the cell, it is normal, okay. And we used, when we were in João Pessoa, we used a vapor of rubidium, and the susceptibility, okay, particularly we are interested here in a real part of the susceptibility, which is signal, okay, sign. When you pass from one side of the resonance to the other. So we call it, in the low frequency side, we call it repulsive, because it will induce correlation, okay, between in the field, which will result typically in a defocalization, and attractive here because it will result in focalization. And so this is the equation of propagation in the field and the susceptibility. And so these are numerical calculation. Here we have our input field. This is a transverse, okay, image of the speckled field at the entry of the cell. This is a longitudinal view. Okay, you can see that each of them is propagating here in the attractive regime, and you can see here a transversal picture of the output field, and here in the repulsive regime. Okay, so you have this focalization, and you have here, you can see a very the appearance of very strong intensities. Okay, and here you have a more homogeneous distribution of low to medium intensities. And here, both in the attractive or repulsive regime, we measure, okay, with a CCD camera, again, the distribution of intensity. So this is the input, which is normal. And we have a deviation from the normal statistics here in the attractive regime. Okay, you have a real increase in the high intensity events. Okay, and here you have only low to medium intensity in the repulsive regime. And this is here also, it's shown the correlation function for the intensity. So this one from 2 to 1 here, the blue one is the normal, okay, the input. And when you have the attractive regime, you have it's narrower, okay, and much higher at the center. And in the repulsive regime, it's wider, okay, and it has a small value, G of 0. Okay, so we are using this G2, for example, to measure. Okay, we are interested in this process of in the attractive regime. Okay, how the focalization will tend to a limit regime. Okay, you can see here that this is the mean diameter of the speckles. Okay, and also it diminishes during depending on the intensity. Okay, and it is constant after from some value of the intensity. Okay, you don't have collapse actually, so it is stabilized. Okay, for high intensities. We are doing this work currently. We have published this paper recently to 2019. Okay, and we have the idea of using this kind of system to make some hardware for reservoir computing. Okay, so the idea is to have a very complex system, okay, nonlinear, which would be our cell. That we can engineer the kind of distribution we put in this cell through a special light modulator. And so we are currently working on this kind of problem. Okay, so calling your attention on the fact that it began in this work in João Pessoa in the UFPE, and when it was published, we already were in our new institution in Recife. So, as I said, I have another. So I already covered the two first parts of my presentation. I don't remember until when I have time because it was delayed. So to do these experiments, we needed a lot of laser instrumentation. So we are really, we can stabilize lasers, diode lasers, okay, with a lot of techniques we have developed, sorry. And from these works on laser instrumentation, okay, this one particularly, okay, when we stabilized the laser with an optical feedback perpendicular to the emission of the laser, okay, we began observing interesting things in the laser, and so we began studying laser dynamics, and so we have here a lot of few examples, okay, of our work in this field of laser dynamics, and rapidly we were also, through the study of laser dynamics, we were compelled to study nonlinear dynamics, and this is what I will talk about now. This is what we are currently studying. So we are studying, I'm sorry, it's still in Portuguese, I didn't notice. We are studying nonlinear dynamics with electronic circuits because it's very easy, it's cheap. You can implement a lot of very different nonlinear equation, okay, with circuits. This is Van der Pol, the circuit, the corresponding circuit. This is Rössler, okay, and we have the same thing for Lorentz system. We are using a system which is Gautier-Bienfang because it was given to us two samples, two circuits of this Gautier-Bienfang by Daniel Gautier, was given to Hugo Cavalcante, who came to work with us in João Pessoa. And so it's a very easy circuit to be able to manipulate. And it was used by Hugo and Marcos in a very interesting paper. Okay, Hugo Cavalcante, Marcos Orea, and collaborators, Didier Sornet, Edouard Hott, okay, and Daniel Gautier, okay, to make some work, okay, on statistics of desynchronization events between chaotic circuits, okay. So we still have these circuits, we are still working with them, both experimentally and numerically. And while still in João Pessoa, we had a few follow-up of these experiments. And what we are doing now is we are trying now to couple one nonlinear oscillator or chaotic oscillator to more than one driver, okay? It's still one unidirectional, okay, coupling, okay? It's one driver, two drivers, okay? And you can have a big number of drivers. And so we study the synchronization of this receiver as a function of the coupling coefficient, okay? And this is varying the coupling coefficient, increasing the number of drivers. Here, as a function of the number of drivers, okay? And we can see, and here this is an analysis of the Lyapunov coefficients, okay? Showing when there is really good quality synchronization in two regimes, okay? Weak regime of coupling, strong regime of coupling, okay? So this is a paper which is currently in a submission phase, okay? So I hope it will be accepted. And to finish on this part, we want to use this expertise we are gaining about this kind of system when you have input from various drivers, okay, to a unique output, okay. And so this is a neuron. You have the dendrites, you have the soma, and you have the axon. And we are currently we are beginning actually in this field, coupling neurons in this Hindmarsh-Rose model, which is a series of nonlinear equations, okay. And we are coupling two or more neurons, okay, bidirectional or only in one driver receiver configuration, and we are looking for some effects, okay. This is here the synchronization between two neurons, and so it depends a lot on the parameters. And obviously, if there are neurons, okay, there are real parameters, okay, existing, and we are using them. And we want to come back to some ideas we had a few years ago about the propagation of neural signaling, okay, as a function of temperature, particularly. We are trying to join these two fields. So I want to finish my talk talking about the mission and the visits first. And myself and Marco Zolia, we had some missions, okay, and visits in the Nonlinear Institute of Nice in the team of Robin Kaiser, in the physics laboratory, the laser physics laboratory, with the team of Daniel Bloch and now Athanasius. And we had the visit of, probably I forgot a few, but Daniel Bloch, Athanasius, Robin, Laurence Pruvot came, Martial, Georges Tredich, Isabelle Morin, and others. And I think our big contribution of us was the student. So we have in the beginning of the 20s, okay, we have the 20s, Pedro Chaves de Souza. He made a sandwich PhD, okay, 1 year in France and the rest in our labs. And after that, he went a few times, maybe for a postdoc. Thierry Passera des Silences was our master student at UFPE, and he went to do his PhD in Cotutel. It means this is the contrary. He spent one year in Brazil, and the rest of his PhD, he did it in the LPL. João Carlos and Michel, they were master students of us before we left to Recife. And João Carlos has done his PhD in LPL, and Michel in the Nonlinear Institute of Nice with Robin Kaiser. And these two are now professors at Federal University. João Carlos and Michel also are working in Federal University. I will rapidly talk about our new campus. Okay, this is a new campus of the Federal Rural University of Pernambuco. Okay, it's in Cabo de Santo Agostinho. This is an engineering campus for now, and so this is the plan. It is under construction. It's not finished. Until now, we have a rented building. Okay, and we are participating, okay, in the construction of the implementation of experimental physics labs. Okay, and so it's not only me and Marcos. Okay, we have a very strong, a very dynamic team here. Wellington, Sergio Barreiro, Rafael de Oliveira, Albert and Reza. Okay, and so also with this team and other engineers from this engineering school, we created, okay, our first graduates program. Okay, it's a program in engineering physics, and so it's very nice. It's very new. We awarded the first master's degree early this year, so it's a very recent. And I was the first director, coordinator of this program until a few months ago. So it's been a lot of, it's very exciting to do this. And so this is the program. Okay, you have here the web page. Last year we had the first workshop, international workshop of our program, and the organizers and the participants received a very kind letter from Dr. Donna Strickland, which was awarded the 2018 Nobel Prize in Physics, because she has a formation in engineering physics, and she wrote a very kind letter to everybody. It was very nice. And this year, we have the second workshop, okay, which will take place in October, okay, in October this year. And registrations and submissions are open, okay? So this is the website if someone is interested. And so I thank you. And as I only want to conclude with, I hope I pass the idea that this collaboration with French teams and also actually with the physics department in Recife, okay, has had a great influence, okay, of our participation, of our building a new lab, okay. We built the first experimental physics lab in João Pessoa. We are building another one now in Recife, in Cabo de Santo Agostinho. We are forming high qualified, okay, human resources. So we are in some way participating in the development of experimental physics in Nordest, as Martial was talking in his talk. So I thank you very much. Your microphone, Tabosa? Tabosa?
Sorry. Okay. So thank you, Martina. It was a nice talk, although your audio was not very good, so we had some difficulty in hearing you. But anyway, I think we got the central idea of your work, which is impressive. I think it's really impressive the effort that you are doing to develop science, physics, and engineering in the university.
Thank you.
Okay, I think we do have time for one quick question. If okay, I don't see any raised hands. So okay, so thank you, Martina, and then we move to the next talk, which will be presented by Professor Hughes-Late. And of course, I'm very pleased to introduce my colleague and first and former supervisor, Professor Hughes-Late, which is a full professor here in our university, and is one of the founding fathers of our physics department. Hughes also has a great and vast scientific career, but what I would like to highlight in this presentation was not about his scientific publication. So I just wanted to highlight, I mean, the importance he played for the development and for the recognition of our department. He was always concerned about our department to have strong contact and interaction with very good and important group, research group around the world. And I think this was quite important for the development of our department. As an example, I should mention that he made the first contact with Professor Claude Pointanucci, which is also a Nobel laureate and honoris causa professor at our university since, I think, 1999. Unfortunately, he could not attend our invitation. But I mean, after this first contact, I think all this long-term collaboration started, and that's why we are here today. So, Hughes, it's a pleasure to have you on the screen, and I think you tell us the rest of the history. So, please.
Thank you, Tabosa. Let me see if I can share my screen with a few view graphs just to Where am I? I'm lost. For a change, I'm lost. How can I find my presentation?
No problem. We don't have a next talk today.
No, I cannot.
If you have your presentation open.
I do.
Can you come back? Okay.
Okay.
Yeah, I can see your screen now.
What I do now?
You just have to put in full screen and presentation mode. Is the third icon on your left? If you come to the left to your right is the third icon.
I don't see my left icon.
Modo de exibição, that way.
Yeah.
Hopefully.
Oh.
All right. Okay. What I am going to do is to repeat many pieces of everything we heard this morning. And well, for me, it's a nice tale, so it's worth mentioning again, telling again. But most of it was already presented. So I'm going to follow with my personal view some of the many years, almost 50 years of research collaboration with French colleagues, and then with other colleagues from other countries relate to this work. The whole thing begins, as already Duclos Martial said, when we met a long time ago at MIT. This was in Michael Feld's and Alain Javan laboratory. For those who do not remember, Javan is the guy who invented the helium-neon first continuous wave laser. About the same time, there was all this kind of work on laser spectroscopy. And Michael Feld, who was my thesis supervisor directly, and who was also connected to our research, was coming to teach in a summer school in Les Houches. And this summer school was organized by Sylvain Lieberman, the late Sylvain, Serge Roche, and I met there many very good people who inspired me. I met Claude Cointanouji, who was teaching there, Claude Fabre, who was attending the school, and so many others. I apologize, I'm not citing everyone who deserves. And what happens in that school was that I continued doing the work of which I already had developed during my thesis. My thesis work is I own to Duclos and Sanchez, supervised by Feld. Antonio Sanchez was a Spanish guy, very nice fellow, a long time I don't hear from him. And Marcelo Duclos, we kept contact all the way. And the subject that I am giving examples was doing spectroscopy of molecular gases. At the time, there was no cooling of atoms, no stopping of molecules in gas form. And so the gas was in a vapor shape, having all sorts of Maxwell velocity distribution. And one game was to select groups of velocities by saturation with a very precise frequency source that was a laser source. In my case there, I was working CO2 lasers in the infrared, and the transitions were molecular transitions. And the molecular transitions, you have rotation and vibration of the molecules. And in this case, with a lot of theoretical work apported by Martial from France, we could separate was alignment of the molecule according to what is rotating with respect to relaxation of vibrations or the rotational level of the molecules. So it was measuring molecular alignment relaxations in ammonia molecules. This is an example of kind of work I was involved in all the time at MIT. Then I should go for France and physics in Recife, physics in Recife and France. And this began a few years later, after 1977, 1980. Martial Ducroix has already explained and mentioned so many people important in establishing this connection. And I am just going to say that my contact with this started with Laboratoire de Physique des Lasers, Paris 13, who now has another nomination, but it's from there. And until today, I still keep contact, even though we have gaps of no publishing, but have lots of fun discussing physics. I should remember Ducroix, Daniel Bloch, Tabosa, Lezama, many co-authors. Some of them I will mention as we follow. What's the type of work done there? One example. I was involved in something that Martial already explained. When we shine light, a beam with a beautiful shape of Gaussian as possible as we can, near resonance into the gas, some nonlinear effects can break up this behavior of the beam by creating new waves. And so the work here was continuous wave, self-oscillation with phase conjugate signals induced in sodium vapor. So this was spectroscopy, atomic physics, and this self-oscillation already insinuated the subject that we heard so much, even the last conference by Martini, which has to do with instabilities. And we also heard before on it. This is a kind of example of work we did in 1986. What another example? Let me see if I find another one. No, I just put that one, but we heard so better explanations by Martial and other people. I'm going just to jump to mention this one here. And I had the opportunity of seeing the Araújo visiting just after me, and we got this work together with the people from Paris 13, which was observing effects of saturation just by the light reflects from a surface. We discussed many times this, we heard about this. As light reflects from a surface, dielectric surface, part of the beam penetrates in an evanescent form to keep continuity of Maxwell's equation condition, penetrates going outside if it's total reflection, or otherwise, but most of the time we are interested in the evanescent aspect of the light in regions that can have atoms or molecules, whatever. And so those atoms or molecules near the surface were a subject of long, detailed studies from the Virtanes group. And we did this work on evanescent wave spectroscopy. But from there, I also had the opportunity within this cooperation with a large group of laboratories that was mentioned by Martial Ducroix, coordinated by Umberto Brandi and Claude Cohen at the beginning, and Serge Roche also. And this took me to École Normale Supérieure, Jussier, Paris 6. And there I had the opportunity of having contact with Gilbert Grambert, Claude Fabre, and various others. I'm just going to emphasize their name. Gilbert, unfortunately, is gone for a long time, but he was really someone special to have the opportunity of collaboration. Let me mention an example of work we have done with him. As I was visiting Virtanes, I came to one afternoon in the labs of Jussier. And what happens, people look for nonlinear interactions of light with atomic vapor in various laboratories. And then Gilbert was also observing the same stabilities that we are observing in Duclois laboratory. And so from his idea, I guess, he contacted Martial, he can correct me, saying that why not, what we should do is a joint publication, putting together everything we have observed experimentally. And as an additional plus, Gernberg put some theoretical discussion that for me was new on how the symmetry of have the conical any angle possibility of nonlinearity. This symmetry was spontaneously broken and hexagons of configurations would appear. And then he proceeded, he also studied the dynamics of those hexagons, etc. But this was the beginning of studying nonlinear structures that came all the way to make like two-dimensional crystals in transversal direction from nonlinear light interactions. This topic, this was a work that we had in 1988. For me, it was great. What else did we have? I guess I should jump to keep on mentioning Jussier, and then I come back to Paris-13. But before, let me say that Gilbert came here to Recife in a visit, and we did have work. We had work with very good students and postdoc at the time. Tabosa, Lorenzo, De Lorenzo was PhD student, then he joined the group in Paraíba. So this shows the scientific people entanglement in so many subjects. This was 89, and really motivated discussions, including Gilbert with the experiments that Tabosa was doing here in Recife. Proceeding with this kind of recollection, I should mention that in Jussier, many years later, after more than 20 or 30 years, close relation and following closely the work of Claude Fabre, we really came into doing some collaboration. We did study a subject that had to do with a paper done with Cid de Araújo, a long way back in 1980, where we discussed the perturbation theory, calculating two photons interacting with two atoms, and examining the line shapes of spectroscopic resonance in those systems. Two-level atoms absorbing light in a nonlinear process of two photons. And this was a work from 1980. Later on, we saw work, and it was Scully, I guess, talking about the fact that entanglement would enhance this kind of phenomenon. We ended up doing some work that involved China by a student of Claude Fabre, and also a Brazilian, from now professor at Belo Horizonte, Pablo Saldanha, who did theoretical things. This work has no experiment in this case here. But those are examples of how we could move around, touching different subjects of quantum optics, atomic molecular spectroscopy, nonlinear optics, which for me was quite nice, seeing people who knew about the things and I could jump around and try to participate in some work. Where do they go from there? It seems blank, but it's not. I should mention the Inside Brazil connections for those works. Claude Lorenz took the route to go to MIT and then is now professor at FRJ. Antonio Cury passed by Brazil and then Recife, and then discovered that going to Jussier was much better for him. Pablo Saldanha passed by Recife and then entered this work, and he's back now to FMG as professor. Marco Orial, we had contact and discussed physics many, many times. Marco, I don't remember if we had paper after France, but I do remember how much I discussed with you, and we had things to elaborate in discussing good physics. Orlando de Lourenço was also mentioned by Martini, and this was connections that made Recife interrelate with various laboratories in Brazil. Those are Brazilian connections, but those connections do not stop in Brazilian things. We have the Paris Uruguay connection. Arturo Lezano, yes. France, Recife, and Fernando de Noronha. For a few who know where this is. It is worth seeing, and I can prove that I'm not lying. Fernando de Noronha. Arturo has been collaborating with us at least twice in the subject of Fernando de Noronha. He could explain. Then we came to the Paris-Russian connection. Marcel de Croix again. He has all those connections with Russia, has done. Tabosa has explained at the beginning, Academy of Science, etc. And he had this visiting scientist, Vasily Klimov, with whom, and Daniel Bloch, we had the discussions about light with structure, not only polarization of the E and B field, but also with angular momentum around an axis, which is a topic of lots of work, as we know, and lots of proposals of applications. And when this kind of light is focused, then we are talking about fields that do not behave as plane wave or simple Gaussian approximation waves, but focus so much that longitudinal and transversal components live together in certain conditions, obeying Maxwell's equation naturally. And those kind of fields that have longitudinal and transversal situation are near a very tight focusing point. One could even say that they have to do with near field, as we talk about materials with charge and have near field. Near field is quite different from far radiating field. But those fields can be created by focusing light. This was known already. And the thing here is that Klimov brought in his experience in nuclear physics interactions, where ultra small wavelength make high multiple interactions appear with photons of lambda that are much smaller than optical. And then we can talk about, see how Laguerre-Gauss beams at tight focusing map in transversal and longitudinal components. One can discuss, and Daniel Bloch, I hope will explain us, because he already explained me. He will explain again all those features relate to these regions where there is no field, but there is derivative of the field. And if there is derivative of E field, we talk about the possibility of coupling to quadrupolar transitions. Okay. And that's why this title saying it's a dark region, dark for dipole, because there is no E field, but there is derivative. There is gradient. Proceeding from that, I am not going to take all my time. I hope you can relax very soon. I should go to another connection. But now is this connection, France, the Institut Non Linéaire de Nice, Jorge Tredich. Argentina, France. Jorge, many of you heard his presence in collaboration with people in João Pessoa, Paraíba. Jorge has an active career in nonlinear dynamics with lasers since the early presentation of chaos in lasers in Italy. From Italy, he did the US, and then from US, he did France, and no way of missing, I had the good chance of meeting Jorge, visiting the Instituto Nonlinear de Nice. Tomorrow we're going to hear Robin Kaiser, who is also from that same institution. But with Jorge, we went in another direction, and let me go for the next thing, which is now bringing us to the most recent kind of subject we are working. It was using diode lasers that can be chaotic. We had part of the research with people from João Pessoa by Martini just half an hour ago. And here is a work where we collaborated with some visitors. Here I should mention Christian Bonato, who is a Brazilian now professor in Rio Grande do Sul. He works through this paper. Cristina Massoli, who is a very, very, very nice scientific collaborating person who is in Spain, or should I say Barcelona. And some other people from Nice, and we did work on examining the spiking pulses from diode laser with deterministic equations, everything, no random terms in equations, just deterministic equation for the laser. And yet we see chaotic, stochastic-like, but not stochastic, kind of behaviors. And then the characterization of those events gave us the opportunity of publishing on the subject. The experimental work was done in Nice. We also had experimental work done here in Recife, and this is about one of my last, I have only two more. But this was in exchange with Jorge. We had even a Colombian student who did most of the experiment, and another Brazilian who is now in the US, Wenderson Barbosa. And Jorge was collaborating with us in doing the statistic of a bursting laser, trying to produce spiking, like the ones that we just saw in Martini's presentation. But here was a laser with a pair of feedback mirrors outside. And according to the size of each arm, the proportion of those two sides could be close to a rational number, 2/3, 4/6, or could be far from those. We cannot prove it was irrational, but it's far from simple ratio of rationals numbers. This has to do with the instabilities of Ikeda from a long time ago. And according to this behavior, the laser instead was showing spikes of chaotic statistics, fairly well behaved, would show spikes with trains of pulses and then empty time regions and everything. And equations do predict this. We still have work talking about this subject, but I do not have any data to show you. I guess by this point, I should be coming to my conclusion. Do I? Yes. Tabosa, how is my time? It's okay. So I better be closing. Why not? So this spanning of 1975, 2021, with all sorts of contacts and collaboration, takes me to a conclusion, which is the following. through this almost 50 years of collaboration with French colleagues, I enjoyed learning physics. But more than that, much more than that, alongside with science, I had all the pleasures to have contact with this extraordinary humanistic culture, this modern society that we all can find as we visit France. So I hope this exchange will continue. We will have a good influence to our students and colleagues younger that will proceed. And to close and to stop here, I thank my French and South American colleagues. That's it. Should I prove it's true, Tabosa? Oh, I told you.
It's already proven.
It's my right. Arturo is a witness. I am not lying.
Yes, that's true. It's true. I testify.
Okay.
I witnessed that.
Yes, Marcial said something. No, Arturo says. See how we hold the fish, Arturo.
Yes, yes. No, I can say that this is absolutely true.
Okay, thank you.
By the way, Rios, I went 4 times to Moroni, not just 2.
Oh, it's not. Yes, you are a 4-time collaborator. How about number 5?
Maybe.
Okay.
Yes. I could only remember the one you came straight from Montevideo, but you had the others that you were collaborating already here. Yes. All right, people. This is my recollection and things I wish to say.
Okay, Hughes. Thank you very much. It was a very, very nice talk. Thank you.
Okay.
We do have time for comments and questions.
Please.
We are right on time. Eh? Very good.
Claudio, your mic is open.
Yeah, okay. I just want to say that I couldn't come in the beginning because I had a defense that I was in the committee. But to say that I profited a lot also from this collaboration, this Recife French collaboration. I was in Rio's laboratory when Marcial de Cloix came and spent some time there, and I worked together with Tabosa and Paulo Oliveira and Petrus and under Rio's supervision. And this was a very rich phase for my scientific career. And of course, I enjoy very much going to Recife and discussing with Rios, not only about physics, but about life, right? Once someone is your advisor, he's your advisor forever, right? He's your tutor, right? On many topics, not just physics, but in real life issues, right? So
you also did Noronha.
I also did Noronha. It was an incredible experience, was really impressive. And I could only say that I'm very happy to be able to come here. Tabosa only gave me only told me about this event 2 days ago. Okay, I only knew about it 2 days ago. So it's very nice to see all of you here, actually. And Rios, congratulations. Huh? Very nice.
We thank you, guys, who helped Recife. Really.
Okay, and any other comments or questions?
I have a question to Arturo. Nobody has question. I always
go ahead. You can ask question. Yeah.
Arturo, that photograph of the animal, I only believe you should show me holding it.
Sorry, what photograph of the animal?
The one you showed in your talk.
That was taken from the internet. I mean, that's not a real photo. No, but we really saw the walking fish.
Yeah, you have to.
That was incredible, Arthur. I do remember that.
Who else was there? I remember you were
I think it
there.
was Licinio. Licinio was around.
Yeah, but there are several persons that saw that fish walking in the parking lot. Yeah.
There we see Jorge from Buenos Aires and Marcos.
Maybe we should
Yes.
continue this
I am here.
Yeah.
Yes.
Hi, George. Hi, everyone.
Hello, everybody.
Hi, Marcos.
I have to comment about not only about my discussions about physics with Jose, but also about football.
Oh, come. Easy. What do you mean?
Well, Argentina, Brazil was always a good topic for us to treat.
We have 1 week quarantine before any game.
Yes. And then also I became, how to say, supporter of this team from Recife, which is the opposite to the one of Jose. How it's called? I don't remember. Wenson can help me.
Not only that, you converted our Colombian students.
Yes.
You converted him in a very tricky way.
Well, it was
Yeah,
really
it was
very
fun.
good to interact with you, no doubt.
Well, if we don't mix up doubts and laughing and having doubts and discussing, we are missing some. We always are. I have a long time experience that this is what we should try. This is what you should try. Yeah. Roban Kaiser, we had some beers in the boat, remember?
You will see my talk tomorrow.
No, you're going to talk about this. My reputation is
Don't spoil my talk.
Yes.
Don't mention everything.
Listen, the talk is very interesting, but I think we have to close the section.
Yes. No,
So,
but
but you can continue. Huh? I just wanted to thank you all for the presentation, and we will see tomorrow. I will see you tomorrow at the same time.
Thanks,
Okay.
Sabosa. No
Okay.
word to say how good is your work.
Okay.
Abraço.
Now we stop recording, and then our conversation could continue.
Laurence.
Salut, Laurence.
Salut. Ah, ça marche maintenant.
Yeah. À demain.
Ça va.
Bon, j'essaie de ne pas oublier cette langue. Hein.
C'est bien, c'est bien. Je vois que vous n'avez pas oublié. C'est bien.
Not Hector, vice Hector, il parle français très bien. Hein?
Pardon, Tabosa?
Ah. Au début, on a eu le speech de vice Hector.
Moi, si, oui, il était en France.